Don't they know I'm busy spoiling myself?
Hey everybody, how are we doing this morning? Squidward is there to wake you up with Project 1. And I've got a new intro tomorrow, so make sure to be here bright and early tomorrow. How is everyone doing? Let's clear my throat. How is everyone doing this morning? How is everybody doing? Everyone's saying good morning in the chat. And it's a good morning. I'm always afraid until I start seeing those good mornings. Until I start seeing everyone be like, hey, there's silence. Pretty good. That's awesome. Scared for the test. Oh no. The test, a few people have taken it. And there's a very bimodal distribution. There are people who have done very well, and there's people who haven't done as well. It's all right. But the biggest thing is, if you are doing all of the quizzes and the test doesn't go well, like someone put in a grade they would not want to get. Like, put in a grade you'd be like, I really wouldn't want to get this grade on the test. So, like, you'd be like, we're going to start with review. Yep. 50. Let's go. 60 is a really good one, because if you were to make a 60 on the test and you did all the work, you'd have an 80 instantaneously. Please, because remember, 60, 100 goes to 80. Just like that. So, even 50. If you were to make a 50... all of a sudden now you still have a C. And making C's on the test, well, then a B in the class is very obtainable, because you're still going to have your quizzes pulling you up. So I know not everyone wants to make a B. I mean, it's not like, hey, I made a B, but it's all right. Like, making a B in a class, especially if it's like, you're like, I don't know, some of it's just not making sense. But you make a B, you're like, oh, God, made a B in the class. But I want us to all shoot for A's. It's like, if you shoot for the A and you make a B, it's not the worst thing in the world. But I want, the grades right now are great. And you want to see? So if you want to see, then yeah, if you're doing all the work, it's like impossible, we said, to not make a C if you do all the work. So keep doing all the work. Keep doing all the work. So I say this because these quizzes, if you know how to do them, they're not, who thought last night's quiz was not that bad? Like, I know I scared everyone. I was like, last night's quiz is going to be so hard, but the grades are great on it. You guys stepped up to the challenge. Yeah, like, it was like, yeah, not that bad. Once you know how to do all the problems, it's like, okay. And then you have to make sure you understand what they mean and like why we're doing it. Manageable. Yeah. So make sure to whatever, if what you've been doing has been working, probably keep it up, because the last 2 or 3 days of homeworks have kind of been at the pace of like the difficulty, I'd say, for the rest of the semester. It doesn't really get more difficult. It's just like, if you don't know how to do it, you'll look at the questions, you'll be like, I don't know what this is asking. You'll be like, I got no idea. And then if you have rounding issues, I think, Keen, you might email me. Make sure to email me and I'll fix those rounding issues. Make sure to like send me a screenshot of where the problem says you got it wrong. And then you guys know I'll fix it up. Let's see. Tyler's going to show us. Let's see if those points are working. Let's hop over here to the other screen, though. Oh, yeah. I'm so sorry I don't have a Thinking Thursdays thing. I was working on project stuff, and we should have the project released tomorrow. Look at all those blank documents. I think I made myself smaller for the Kahoot. There we go. That's about the size. There we go. Okay. So project. Streamlabs, you there? Streamlabs, you okay? Uh-oh. Streamlabs, you need to get in gear, or I'm going to have to be giving her, I'm going to assign points manually later. Let me see what Streamlabs is doing in the background here real quick. It says it's working. I'm gonna reset. We'll give it its time. We'll let it do its thing. Let me try Streamlabs again this way. Take a quick look at this. Okay, it says CloudBot's on. We'll give it to like 9:10 to get in gear. So what are you doing, Streamlabs? Maybe it's their side where they have all these random issues, because we had that one day where on Twitter they were like, yeah, we're being weird, Streamlabs is acting up. So we'll give it its, I don't know why sometimes it would do it, because it's supposed to be running on OBS. I should not have, everything's still right? I clicked CloudBot within OBS. Okay, that says CloudBot's on now. Okay, now I'm back to... Okay. So let me try it again here. Okay. Let's talk about the test here. We'll explain how the Streamlab points work again. So it is if you obtain, and if we don't see Streamlabs working by like midway through the stream, I'll be adding points on. Don't worry. I'll have you guys send me the points if it doesn't work. So it's 1,000 points. I put it way too low, but that's the way that it goes. It's 2 points on your final grade. 2,000 is 2.5. 3,000. Did I say it was 3? I think I did. Ah, it's not 30,000. That is how it works right there. And we'll hope Streamlabs starts working on the stream. It'll be the first lab it doesn't work, which hasn't happened yet this semester, but we'll hope Streamlabs does its thing. Why is it not working? So I put the points way too low, but I'm okay with that. I'm still practicing these things, figuring out how to utilize them best. And so that's what we have. If it doesn't work, stay the whole time. And I will give you points at the end, but you'll have to be in the chat and you'll have to say, hey. So I promise I'm not doing this on purpose. I really want Streamlabs to work. It's the easiest way for me to record points. And then even I've been trying to... I was trying yesterday to no, that was a few days ago. I was trying to assign points by like doing it in the chat. I wish I could. I wish I could just click names and then add points. Like be like, plus this to a person. It'd be so easy. It'd be so cool, so easy. I like that you guys can track your points if Streamlabs wants to work. So give it another 3-4 minutes. It should start working. So remember, though, here's the biggest thing. With the extra credit, this is where, don't worry, like I'll get an email. So we got to hope Streamlabs is on its game. Sorry, sometimes it takes a moment. Sometimes Streamlabs takes just a few minutes here to boot up. We've seen that where first 5 minutes of Streamlabs is being all weird, and then 5-6 minutes later, it actually starts working. But remember this. Well, the points are still in the background. I still have them. And I will add points if we need to. But if you have an 87.9, we're going to talk some sad stuff here for a moment. And you get, let's say person A, they have the same grade. Person A has 2,200 points. And person B has... this would hurt me. I mean, I've seen things this close, but I figure I do these things this way so it's very exact. What would person A's final grade be in the class? I'm very exact in how I do this. Also, you kind of have to think of these things. They would get that. A would have they'd have this, and they'd get an A minus. B would have an 89.9 and they'd have a B plus. What if this is person C up here now and they never attended class? They never attended class. That's their grade. They'd have a B. So when you look at this, it's a big bump to your grade. It's a big bump. Now, a lot of people usually aren't on these very borderline things. But the problem is if I does it make sense? Like if I were to bump them up, I would be adding even more to it, but there's already a big increase to your grade anyways. So it's 92, Christina, 92. So none of these people could get up to the 92, which is okay. I mean, the 87.9 and the one person being an A minus, that's awesome. So there's a big... by participating, by interacting in class, you get a pretty big increase to your grade. So there's a pretty good, extra points. If I had the 3,000 then you'd get it, Camden. Yeah, if you got an 89.9, and so no, well, this person right here, remember, all these people have this right here, and then this person's bumped up to this person's bumped up to this. If you had an 89.9 and you have 2,000 points, you would get the A. So does that make sense there, Camden? Hey, Streamlabs is back. Streamlabs, Streamlabs needed its coffee. Gracie was the first person to get points. She gets an extra 20 points on these Thinking Thursdays. Gracie knew when Streamlabs would be working. Everyone's checking. We started an avalanche of checking points right here. And so keep being here, keep interacting, try to get to that 3,000 points. We will do another big Kahoot at the end. but being here, interacting, getting all these points, really awesome. And so just keep being here, keep talking, keep interacting. Best way to get your points, and that's good. And a lot of people are already beyond the 1,000. I should have put it to 2,000, but lesson learned. But I told you guys, and my word is good on it. So because it's like, if I could redo it, I would be like 2,000 and like 1,000 is 1 point, 2,000 is 2 points, and then I'd probably put 4,000 and 5,000 or something like that. But the points are what the points are. We decided it, and that's what it is. So a lot of people are getting a major bump, and I really appreciate that you've been here, been interacting. So that's how we do the points. We know what's going on. Streamlabs is back. 40,000 is 4 points. You have to get 40,000. Watch me get someone 40,000 points. No, there's no 4 points. But you guys make the stream, Thomas. You guys make it. Thomas, 20 points right there. And remember to email with those points that are extra points. But let's all spam the chat. It's on a delay, so you can't get extra points for just like boom, boom, boom. But you do get points for talking. So awesome. So great job. Appreciate everyone here. With the test, well, 2 things. Project will come out probably tonight because I want to release the project tomorrow, so we can we won't do a full stream on it tomorrow, but we will at least kind of talk about it. And I want you to kind of work on it a little bit on your own, but not like, if you're stuck, just put it down, look through the questions, work the ones you can. I want you to do it this weekend a little bit. And then we're doing a bonus stream on Monday. It's not a required stream. The project will be due Monday for extra credit, and the project will be Tuesday for regular credit. Now, what should you do if you want to maximize your grade in the class? 20 points first person who's going to give some advice to the class. I said the project's due Monday for extra credit and Tuesday for regular credit. What should you do? Monday at midnight or 11:59? Because Monday at midnight is technically, like Monday morning. So 11:59 Monday. The way we talk, yep. Let me see here. So Morgan, and how much extra credit? I think 7 points on the whole project. Turn it in early. Keen, you're right. 20 points right there. Keen's first say turn it in early. Turn it in early. Turn it in early. Please, please, please. I would love it if everyone turned their project in on Monday night. That'd be awesome. Like, it won't be that much different doing it Monday than Tuesday. Also, we have Monday off, so we will do a stream on Monday. You're not required to watch it. It's me helping out the project. So I will work the project on Monday, turn it in on Monday, get those bonus points. It'll increase your grade. But if you don't do the project well, don't just turn it in. Like, if you just I'll just guess and do random things, don't do that. Are there any big ways to mess up, or any advice? Cheating. Cheating is the worst way to mess up. Don't cheat. Don't copy anyone. Don't send your work to anybody. I check for plagiarism, so don't use anyone's project from a previous year. I am altering the project, but don't, one of the worst things people do is they have a friend who's taken the class. They then take a project someone's used. They try to alter it, but I told you I've been teaching for a decade. I have a decade of projects, and I run all the projects against a decade of projects. And you might say, well, might you get some false positives here? Usually when I get, and the only allegations of plagiarism I put forth are the ones that literally we have things like 98% matches, where your project will match someone's 98%, like 98% of the words in your project and the order of your words match. And for some reason, sorry, I'm going on a quick rant here. Night, I went to the store and I bought tons of donuts. I saw it. They were really awesome, and I thought I should buy more donuts. I don't know. I want donuts. So when we see 98% matches, someone will write something like this, and then the person will go in and they'll be like, they'll go here and they'll change this to drove. And then they'll put lots. I don't know how they think our plagiarism checkers work, but they'll add a word here, and then they'll change the context of another word a lot of times. And we usually go for ones like this that are there's ones that are iffy where it's I don't know, but I go for the ones whenever we make an accusation where it's really, you wrote, yeah, and then they'll add grocery. You'll see it and you'll be you really came up with the exact same. Yeah, you missed and then you'll see typos and stuff like that. You'll see typos. You would see this. You would see both people misspell grocery. You'd see that there'd be just word changes. You see number changes. You see these very little things, and you're you wrote nearly identical to somebody who maybe took the class last year. And one, if you ever get caught cheating, please just admit it. It makes our life so much easier, as in it's not fun making accusation of cheating. Two, the best way to not cheat or get caught cheating is don't cheat. So don't cheat. It's not fun for me. I hate it. I hate being serious. So don't do that. Just don't. So, okay. The project I don't think is that bad. I don't think it'll take 2 to 5 hours. And when I say 5 hours, that's the extreme, I think. But if you watch the stream, I think it'll take about 3 hours. So I'll go through it during the stream, be working on it, be asking questions. I'm not going to work your exact questions, but have time dedicated to this project. Like on Monday, be like, okay, I've got Monday off. I can sleep in. I don't really have to be learning anything on Monday, like anything new. There's no new material on Monday, but be like, okay, I need to complete the project on Monday. So maybe I should attend the stream live. I should be working on the project in the background. I should ask Brian questions when I'm stuck. If I watch from like 10 to noon or like at some period, be hopping in, be asking questions, I can probably get most of the project done. I can have the project done by like 3 that day. So I would say you can get the project done that day. Does that make sense? I think we should be good. Like, I think if you start watching in the morning, ask questions. You could do it in R. I personally, if you have not used R yet, I would not suggest R. But you could. I mean, if you want, we'll email you. If you're like, I'd really like to learn some R. I would say it would take 3 to 7 hours if you're using R. I mean, I could do it even faster in R because I've been using R for a long time. But with the learning curve, I would not suggest. If you have a way of doing the whole thing in Excel, I will accept that. I would not be the best help for Excel because I could figure it out. I mean, you can ask me questions. I'll try to help you. I will accept whatever you do the project in. And I haven't posted it yet. The project, I will post it probably via email. It won't be posted on the site. So expect an email with here's the project and here's when it's due. I mean, Monday night, extra credit, Tuesday, regular credit, and the test is due tonight. I would say the best way is Jump, and that's what we'll be covering on Monday. It's pretty easy on Jump. Technically, my brain's saying it's even easier on Jump, just because I've done the project so many times in Jump. So I might even be able to do it quicker in Jump. I can do it in R, though. So, yeah, because I made it. There'll be a pivot table pivot chart on the project, and I figured out a way to do a pivot table pivot chart in R, but it required a lot of code. It's like R isn't set up to normally do those, but I figured out a way to do it inside of R, which took a lot of code. And I showed Dr. Petrie because I was so excited. I still get to be like that. Hey, look what I did. Look, I did this. It's so cool. And he's like, that's nice, Brian. Good job. He's one of the people who taught me how to code. So I'm excited whenever I get to show him something. It's literally like a kid being like, look at me. Brian's a big kid. Okay. So project is coming up right here. The test is tonight. What chapters do you have questions over on the test? Oh, decision trees. People are wondering about decision trees. That was a big question yesterday. I like decision trees. Let's hop here and let's talk decision trees real quick. I would say the number one thing, what's the best? Oh yeah, we got that one. Yep. Decision trees. Decision trees take what kind of data? Just doing a quick review of decision trees right now. Decision trees take what kind of data? And we'll do confidence intervals and margin of errors here in a second. Yep. I think yesterday's review, the Kahoot review, is really good over everything but confidence intervals and decision trees. So we could cover those two right here. So the Kahoot review, Thomas, covered everything, like a really good review of like probability, simulation, sampling methods, and then we're just missing a few right here. So categorical and quantitative, you're all right. The only thing it doesn't take is identifiers or things that act like identifiers. Thank you very much, Devin. So it takes categorical and quantitative. It doesn't take things that act like identifiers or actual, like, so it shouldn't take this because that's actually an identifier. So we're going to take all of these right here. And there's a few ones we want to remove because they act like identifiers. We want to take out somebody's favorite phone app because that acts like an identifier. And then we want to take out somebody's major because that acts like an identifier. I'm putting all of these into the X. Yep, the Kahoot should still be posted, Valerie. It should be the second to latest video. Go to videos, and it should still be posted. Good questions. Wait, did I win the $10? Yeah, the Magic Giraffe won. Magic Giraffe just destroyed it. Magic Giraffe. was magic. Oh, it's magic. Giraffe. I gotta stop singing. Got problems, guys. Let's look at what are we going to predict today. What are we going to pick today? Whether or not people... There's so many things to predict here. I've done so many of these that I know the ones that are bad. Jump is free for students. Yep. If you have issues downloading it, just tell me. Devin got the 500 points from Nealon. Yep. Let's try to figure out how many languages someone speaks. This might not be the best one, but let's see. We're going to predict how many languages someone speaks right here. So if you notice, we have a quantitative Y. Why does the data look like this? What do you notice about this data right here? What do you notice about this data? Like, just analyze this real quick. It's actually kind of like a dot plot. Dot plots are quantitative. We could maybe put a histogram on the side of it. But this is a very, very right or left skew distribution. This is very, very skewed in one direction. Because this is one quantitative Y variable up here. This is very, very skewed in a certain direction. It's probably going to be a horrible decision tree, but I was like, let's do it. Just look at this data here. Look at this data here. Right skew, you got it. Cooper, Thomas, and Valerie, 20 points. It is right skew because it's right to the high, left to low, whatever way that tail goes. And the tail would go this way. It's a little bit hard to see. If you're wondering, we can go to Analyze, Distribution, Languages. You can actually search, and I always forget that because Jump used to not have that. So you can see it's right skew right here. So we'll stack it, and now it's right skew. This is the same data being displayed in this Y variable right here. So that's the one. So you can see here's 1, 2, 3. And you know what's weird? This right here is a box plot because this thing right here is a box plot, and these are outliers. Anytime someone says to you, I can speak 2 languages fluently, what do you think? Which I should say as Americans. Kind of questions like this here, Claire. Like, we did a little bit of theory stuff, like decision trees can take quantitative categorical variables. They don't take identifiers or things that act like identifiers. Thomas does not believe them. Cooper says Coolio. So yeah, anyone who can speak 2 or more languages fluently is an outlier. I know that sounds crazy, but at least here in America, if you're like, I can speak 2 languages, people are like, whoa, you can speak 2 languages? You're like, yeah. And I mean, in other countries, it's more common. There's a lot more borders. Like, you go to like Spain and then you travel a little bit and you're in France. So you can French and Spanish and all these things. So there's more overlap of communities such that it's more beneficial to have another language. And there we go. Camden can speak German. You're like, whoa, Camden, you can speak German? You'd be like, wo bist du? That's about all I know. Or Einstein, Freien. Or, mein Elken. I don't know. I really like, there's some quotes from X-Men. Man, you got to watch X-Men First Class. 9. So, you guys are cracking me up in the chat. My grandfather, I think I told you guys that, Manfred Schwabacher, he came over during World War II because our family history is Jewish. So, but Manfred Schwabacher changed his name to Fred Stevens. Manfred Schwabacher. So I think it's Schwabacher. So I'm Brian Schwabacher. So all the different languages in the chat right now. When my brothers were little, elementary school would teach Spanish. Yeah, Dankeschön. Yeah, that's German, right? For thank you, Dankeschön. So I like learning other languages. Like I like I try. Chinese is so hard. Like we ni hama. So hopefully, if anyone knows Chinese, you can be like Brian. You just we ni hama. I say to my fiance, I say why ni. Oh, let's see. There's Dutch in the chat. All these languages. This didn't turn out so horribly. It turned out kind of bad. Japanese? Oh, that's awesome, Devin. I don't think all I know is like Domero Gato. Like, thank you very much. Like music and stuff. You know what's interesting? That's my last little sign on this before we get a little bit more serious on decision trees. Music and such really you messing around, Devin. Well, anime, music, video games, all that stuff can really help people learn other languages. And so it's really kind of, kind of how we bring the world together with like literally like, it's like, bring the world together with music. But I mean, we kind of do. with anime, music, video games, movies, all these things can really help make the world a much smaller place and realize that we're all just people. Yay! Life lessons with Brian. Rainbow time. You know, I wish I could speak more languages. Yo estudio español en la escuela. Muchos años pasado. Después de yo trabajé en el restaurante. Es muy bien, porque muchas personas hablan español con me. So, yeah, I like that. Yeah, that's the thing, is like, just make the world a smaller place. You can speak 3.5. Yeah, feel free to put them in the chat. And this decision tree doesn't do that great of a job of explaining what languages people speak. The number one thing that has us. Oh, well, look, people who are not texting, but this is such a small group. Yeah, it's like, well, start today. The sooner you start, the more likely you are to get on track with it, being able to speak another language. So, Camden, that's too funny. That's too crazy, Camden. The number one thing for figuring out if somebody's in a relationship, let's do it. The number one thing for figuring out if somebody's in a relationship. Oh, we already did this one. It was age, wasn't it? It is age. We did that one. Okay, we got to do a new one. Does everyone see what the decision tree is doing, though? Do you understand the point of a decision tree? Which I wish we covered more. Like, what's the point of it? It's to explain the Y variable. It's to understand the variation within why people are in a relationship. And so we can pick any variable we want. Okay, you guys got to help me out. Tell me a number. I'll pick the number you say. What number are we going to pick? It's on the graph. William. 7. I'll do it. Okay. Greek life. Why are people in Greek life? This is real data. And so however it turns out, not responsible for because it's real data. Okay. We got 72. There's no 72. Split here. How far they live. Didn't we do this one? How far they live from campus. I remember this. So it's how far you live from campus. It's your family economic status. We did this one. And then it's whether or not you've drank. We did this one. Yeah, we did this one. Okay, 12, someone said. That was the one we did during class. So we've done that one. And let's do 12. Let's do 12. What's 12 say? It's really cool because if you look at how it's actually what the decision tree is, how much you spend on pets. Well, that will be how many pets you own. I've done it before. 16 and then 23. 16 is family economic level. Yeah, that's cool. Let's see why their families are in different economic levels. We've got here upper class, middle, upper, middle, lower, and then lower, middle, and then lower. The first split, and so here to go to Josh's question, the first split is, do you have student loans? And but the thing is, this only explains 4% of the variation in your economic class. But if you look at it, we've got the yes group over here and the no group over here. And I want you to look at this kind of orange-brown. It's not a nice color. It's not like UT orange. But do you see this orange-brown right here for the people who don't have student loans? Because this is the no group. This is the no leaf. And these are the same people. This right here is the same group of people over here. You see how there's 732? That's a little bit bigger than this 576 right here. Being able to identify that this group right here is this group. Now I can split it again, and now we see that this group, do you see this group we just saw? This group right here that I'm circling is this. Now watch it split. It doesn't have to split in half, but it kind of does just because it did that. Now it's split into this group and this group, which is down here. So it's splitting apart, and it literally almost split directly in half. It doesn't have to. Yeah, and I'll throw some life advice after this. No, it's a good question or a good thing. The interesting now goes on economic, but the variation's not going up that much. It's only 5%. So let's split again, and now it's whoa. Who'd have thought that it is? There's a lot dealing with political affiliation. I mean, it's in the survey and it's choosing it. So you can see here the people who are most likely to be from the higher classes. Okay, here's upper class. Well, you see it's economic. It's economic. So, I mean, that kind of makes sense. Like, it doesn't mean if you have an economic view, you'll be from a certain class. But think about this. These people over here are the ones who report, and this is self-reported too, that they are from the upper class. And kind of nebulous terms like, what does upper class mean? You might be like, oh, if you make 200,000, but then if you go to someone who makes 200,000, then like a family, what is the family? Is it an individual? How big's your family? It's so nebulous. like hard to nail down what it means to be upper class. Like we should have just said how much. We don't want to get too personal with these things. How do we tell the variable is impacting the data the most? It is the first split. That's the one that is attributing the most variation. So the first split right here, student loans, is our best indicator. See, and then, but if you go to someone who makes 200,000, they might be like, oh man, I'm not making that much. The people who make $500,000, and they go to someone who makes $500,000, they're like, oh man, those people who make $2 million a year, those people who are pulling $1 million a year, you're like, what? It's pretty crazy. It's, really, the more money you have. Brian's gonna give some life advice after this. I'll give it right after this question. I'll finish this question. So we have here, let me show you all the important things you're responsible for decision trees before I give life advice. We've got leaf report. Oh, good. It's almost on the screen. I hate it when it goes off the screen. And then we have split history. Where's split history? There it is. What does the split history show you? Like, someone break down in words for 100 points, what's the split history show you? Because these are things you are definitely responsible for. Well, I won't get rich. Smashing the like won't get me rich. It'll make students rich. I never want anyone to think Brian's doing this for his own success. When I saw the one comment that a student made, like, Brian wants to be a YouTube star, the only reason I would want that is so that the channel makes more money and we can, like, once we get our first $100, I might just, like, try to give it to a student. I might just say to UT, can I just be like, hey, we got our first $100. Can we do, like, someone gets $100? We do a $100, like, help out a student who needs it. So, like, do, like, a merit scholarship. That's what it is. Or, I guess, need-based. That's what it would be. I'd love that if we could do that. So I want every dollar we make from YouTube to somehow go back to students, whether pizza parties, tutoring, or scholarships. Yeah, and I don't expect to make a lot. And if we do make a lot, then we'll just, and UT's been very nice to me. So, yeah, well, you can, yeah. We might say, like, 4 more current 201 students. If we have, like, 400 students apply or 500, then I'm sorry, it'll be, I don't know, you could get it. And I think $100 wouldn't be that bad. So, well, thank you, Devin. I just don't want people to think I'm doing this to be like, hey, when you smash like, my channel's, it's our channel. It's our channel. Like, if you guys didn't watch this, right now we're making about 30 cents a day. But you know what? 30 cents a day is about $100 a year. So we could do it. During peak times, we made like $11 a day. And I was like, whoa, because $11 a day, that's $4,000 a year. And if we're pulling $4,000 a year, then we're giving out, like, 4 $1,000 scholarships. So, but that was just because everyone was watching. Never gonna do the president thing. So here's everything you're responsible for this. I would not put output like this that goes off the screen, but please notice that the leaves are the very bottom as a fire truck goes by. Does everyone see here? This is leaf 1, leaf 2, leaf 3, leaf 4. Thank you very much, Jack. Leaf 1, leaf 2, leaf 3, leaf 4. Leaf 1, leaf 2, leaf 3, leaf 4. Go away, fire truck. Leaf 1, leaf 2, leaf 3, leaf 4. Does that make sense to everybody? Do you see this 4 right here? 4 lower class right here. This 4 lower class is the start of leaf 1, and it is very hard to see. It is literally these 4 red dots down here. I can make it big enough that you can see them. It is these 4. I'm having a hard time seeing them. Yeah, it is. There's 4 red dots. 1, 2, 3, 4. You can count the green dots. 1, 2, 3, 4, 5. And then go back to here. 4 lower class. 5 lower middle. You could go to the 91 middle, and that's where you start to see this right here. There's 91 dots inside of here. Now, it's hard to see right here, but there is a red and a green right here, but it's so small, you only really see the blue, which is above it. Does everyone see how this whole thing right here, does it make sense? This right here, which I'm highlighting, is also this right here. This is the same thing, which is also all of these numbers or all of these percentages right here, identifying this as leaf 1, and then identifying this as leaf 1, and identifying this as leaf 1, that all these things are giving the same information but in a different way. That is what is so important. And if you understand how to read this and what it's showing you, and once again, 20 points for the first person who tells me that all of these things here, like this, and these are showing me the distribution of the what variable. And you only have to type something very quick to tell me to get your 20 points. All of these things are showing me the distribution of the what variable. It was how I ended the lecture, one of my last questions. You got it, Sarah. Boom. The y variable. Yep. Sarah and Hannah, boom, 20 points right there. And Claire, let's do it. You guys got it. It's the y variable. It's the y, because let's double check. You ready? The y-axis right here is family economic level. Does everyone see this is the family economic axis or y-axis? And then down here are the x variables. So these are the x's, and the x's explain. So the x's is how we're splitting it apart. And then you can see the x variables here, but this right here is the distribution of the y, which is family economic level. So it's giving you the distribution of people's family economic levels within each of the leaves of the decision tree. And so that's what's going on with decision trees. Does that make a little bit more sense to people? Like, know how to read this, be responsible for everything on the screen. So that's what I would say. So yeah, so Sarah, 20 points against Sarah. So decision trees are really good if you have a lot of x variables. They're very, very advanced. And I don't say that in a scary way, like they're super advanced, but they're a complex algorithm which can find out, they can take all of your x's. Like you could give a decision tree 1,000 x variables, and it would look through and figure out which x's are the best x's and how to split apart the data based on those x's. So it's doing really complex algorithms in the background for you to figure out how to use each x and how to explain your y variable. So if you were to show this, like if you were in a class where you collected a whole bunch of data and they were like, we want to make a model to explain this, you could say, well, let's try a decision tree. It's also called a partition model sometimes. And so, yep, and it literally, what it does, let me tell you what this tree is doing. You ready? When you run a decision tree and you make this split right here, what the decision tree does is it's going to look at how many of your variables. When you say make a split for me, the decision tree goes and it says, okay, let me look at all of these variables. The decision tree looks at every single x variable you gave it, and then it says, okay, this is the best variable and this is the best spot to split in. So it literally, we gave it like 50 variables. It looked through every 50 variables like, oh, no, 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 here's the best one. And then it's going to look within this one and this one, and it's going to look at how many variables. Now it's got 2 spots. So it goes over here and it looks at every variable and every spot to split the variables. And then it goes over here and it looks at every variable and every place to split those variables. It says, here was the best spot to split. Then it goes here and looks at every variable and every spot to split those variables. Then it goes here and looks at every variable and every spot to split those variables. Then it goes here and looks at every variable and every spot to split those variables. And it says, okay, here was the best spot to split. So every time you do this, it looks at every variable and every spot to split the variables and tells you the best choice. And it does it for you. You just hit split and it's like, okay, here's the best thing to do. That's so cool. It's so complex. And we don't have to do anything. It just does it for us. So it's trying to split apart your data. Think about this. I'll make a very, very simple one really, really quick. Okay. We're going to make a taste scale for cookies. And so we're going to put here some really tasty cookies to start. They got 9s. These were good. Oops. I'm going to make this kind of obvious. Okay. Sure, these were bad. Wow, so many bad cookies. Sure, it's easier to do if I do it this way. So now we're going to go here, and we're going to go to chips. And we're going to go to yes, 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 no, 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 yes, yes, no, 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 no. Can everyone see that the cookies with chips got much higher ratings in general? I didn't make it perfect, but generally we see that cookies with higher chips got higher ratings. Let's go here to burnt. And we're just going to do something super obvious. Super obvious. That's going to come out as like our number one thing. It should. And let's go here to sprinkles. And so kind of made this one random. Cool. This one's meant to be pretty random. I don't know what's going to happen with it, but if I had to guess what's going to happen with this decision tree, what do you think? I'll put yes on these last two. Where do you think this tree will split first when this tree tries to explain how tasty the cookies are, 9 being awesome, and no being 1 being horrible. I think it'll actually split on whether or not the cookies are burnt. So let's go to predictive model, partition tree. Let's put in, we want to explain how tasty the cookies are with these variables. And now we've got, you see, here's the average tastiness, and we split, and it was whether or not the cookies were burnt. So when you look at the data, you can see, and I purposely made this like a very easy to understand example, but 91% of the tastiness of the cookies is explained by whether or not they were burnt. And then the next thing, oh, it won't even let me split because I've got too little data. No. There's too little data. You know what we could do? Need more data. There we go. More data. More data. Repeat observations. Let's do it again now. If you have too little data, it's called min ops per node, but don't worry, I'm not going to be testing on that. We got more data. Split. Okay. So now it's if there's chocolate chips and 91.4, 91.6. I don't even think we should split because if you look at this, look at how little the R squared goes up. Does everyone see the R squared went up from 91.4 to 91.6? Yep, it's on. It's not on Canvas. It's on. If anyone puts it for Valerie, where it's at, you get 100 points. First person who put the Stat 201 exam page up for Valerie. And then it's sprinkles. It could split over here on sprinkles now, which it might. It's got it because it's the only variable. So you can see things repeat, but look at the R squared. So, when do we stop splitting the tree? Thank you so much, Claire. Claire, you're awesome. And then go to the test page on that, test 2 page, and it should be up. If you go to the split history here, you'll see that we're not really seeing an increase in R squared. Does everyone see that the R squared is not going up? This is what split history shows you. It shows you the history of R squared after each split, and we're not seeing R squared increase. Taylor also gets the 100 points. Thank you very much, Taylor. So I think it's pretty obvious right now that the number one thing that explains the tastiness of the cookies is whether or not they were burnt. And we could ask if the cookies were bought. So we're selling the cookies now. A little bit of randomness. Is that the 20? And then we repeat it. Okay. So I just did this so we'd have more observations. We could actually run it a little bit more because decision trees get mad if you don't give them enough data. So now I'm going to see whether or not the cookies were bought. And I'm very interested to see how this turns out. It'll look a little bit different here. We'll color the points. The blue cookies were bought because we're trying to explain if the cookies were bought. And actually, people are buying them based on chips. All of my chip cookies were bought, were they? If they have chips, every cookie was bought. That explains 61% of the variation. And then sprinkles. These are cookies right here with no chips and no sprinkles. And then you go down here, and it's how tasty they are. And this explains 73% of the variation. So people were more likely to buy my no chips sprinkle cookies if they were tasty. So, but the number 2 things, which, it's so crazy. This kind of makes sense because I'm surprised burnt got on it. Maybe it was like the bottom of the cookies were burnt. We'll say it's like the bottom was burnt because I don't think people would be buying burnt cookies. I think if it was burnt, they'd be less likely to buy them. So my data's not perfect like real world. But this would, if you got this data, what would be the number one thing what would you decide based on this data? I really like this. Man, I wish this was the project right now. Maybe this is the start of the project. Stay tuned because I think I'm getting some project data right now. You work at a cookie company and you are trying to make the best cookies that will sell. What decisions would you make? I might just start using this. What decisions would you make from this data right here? That I would say there's some big decisions I would make from this right now. If you looked at your data and you saw this right here. Not from this. You would think don't burn the cookies. And that's kind of cool because it's like a reverse of what we have. Claire's right. We need, like, all of our chocolate chip cookies sell out. I would say, like, well, we obviously need more chip cookies. But the thing is, from this data alone, you wouldn't say don't burn them. I mean, don't burn them is kind of obvious. I mean, you probably want to do like customer satisfaction surveys to see if they come back, because if you burn the cookies, they might buy them, but they might not come back. So business analytics is not as easy as just look at data. You have to then go beyond it. You have to say like, well, maybe we'll lose the customer if we sell the burned cookies to them. Like we have to look at customer retention. So like, even though we might sell the cookies, will we still be able to sell the cookies to someone again? So chips is the number one decision. Like, you think appearance matters when you try to sell an item, like how it looks. So people are buying up our chip cookies, like the chocolate chip cookies, those are selling off the shelf. But then you see if it doesn't have chips, the number one thing that's going to help us sell it if it doesn't have chips is the sprinkles. So the sprinkles right here would be the kind of like, if it doesn't have chips, it should have sprinkles. The cookies we're not selling right now are the cookies that don't have chips and don't have sprinkles. So literally, if we just have regular old cookies, they're not selling. All 15 of these, all 15 no chip, no sprinkle cookies did not sell. Blue means they are bought. Yep, blue means they are bought. So you can see that. Great question, Claire, 20 points right there. Good question. Oh, Hannah was asking it. Hannah, 20 points also, and Claire answered it. Yep, thank you very much. So remember, it's the distribution of the Y variable, which is bought. So the blue and the red are the distribution of the Y variable. And you can go here to leaf report, and you can see the whole leaves of these. Will it be blue on the test too? Yep. Or we might make it black and white. Sometimes we do grayscale. It'll be pretty obvious. You just have to look right here and see what colors are here, and then see what colors down there. So no, it's not too much info. I think it's grayscale though. I hate that. I wish we can show colors now. Why don't we? I think it's grayscale, which you'll be able to tell. It'll be like a darker gray and a lighter gray. And so it'll be like darker and lighter. We also do it too because people are colorblind. Yeah, that's why. So if someone's colorblind, if we do like a darker color and a lighter color, like dark black and light black or light gray, it's easier for them to see on grayscale, because red, blue colorblind people will have very, very tough time with this. It'll be very, very confusing. But if you do like dark black and light gray, everyone can see that. So, and yeah, it's really tough. I've had a few colorblind students, and they'll call me over and say like, which color is this? And I'll be like, that, and then I'll realize it. I'll be like, it's blue. And I'll be like, oh, red, blue. Why do we do this to people? I'm wearing a red, blue shirt. So that's got decision trees. Okay, we have one more thing we're going to talk about before we, confidence intervals. And then we're going to get into today's material. But Brian's life advice. Okay. I want someone to come back and maybe thank me for this later if they follow this life advice. If right now you are buying like Starbucks every day, which we're not on campus. I know, fun times, right? But I say this to people, like, if you can find a way to cut out $3 to $5 a day, $3 to $5 a day. Actually, it's for every $3, because that's the big thing. Every $3 you save a day is basically what a year. Every $3 you save a day. Split history is the history of the R squared, Claire. Great question. Split history is the history of the R squared after each split. Great question. Every $3 you save a day is basically what a year? Basically 1,000. I mean, it's over 1,000, but it's over 1,000. So when you think about, a decent drink at Starbucks, not like a huge frappe or stuff like that, not a huge frappuccino, but you, just pretty good, like coffee double shot or something like that is probably like $2.50, $3. Every $3 you save a day is over $1,000. And I think that just amazes me too. So when I realized this, I realized like every dollar, and that's like what Dave Ramsey talks about, is like every dollar. So I hope Camden, I hope your internet's working fine. Yours is paused too? I broke the internet. They don't like me talking about this. Are we back? There was, click the bottom thing, click the bottom scroll wheel. One of the channels I was watching last night all of a sudden got cut off. I don't know if YouTube's being weird or what. Awesome. Click the bottom scroll wheel. Just so people know, they would not know. All right, click live. Yep. Does everyone see at the bottom of the screen right now, there should be YouTube. You need to get your game together. Happened to another creator last night. There should be a scroll wheel at the bottom of the screen that has settings. And awesome. And then there's the live button. So every once in a while, you might need to click the live button or click the scroll wheel with settings and go to like 720 or 1080. I think are we broadcasting in 1080? Who can tell me? Do you have the 1080 option on here? When it came back, it was 360, now it's 720. You're good. Yeah. Yeah. And just change the, yeah. And so we're using, it's actually a 4K camera. So I wish I could, yeah, but we have 4K capabilities, but yeah, mine's 240. Awesome. Well, yeah, it's so weird. We had this weird thing yesterday. I think that was a YouTube hiccup right there. But I pay Comcast for like near gigabit internet. They're like, your router's not gigabit. And I was like, I literally bought this router on the phone with a guy saying like, can this router handle gigabit? And he was like, yeah. And then they're like, okay, well, you can have 500 megs at the moment, 500, whatever. I don't know. Okay. 240. If you put it on auto, YouTube will change it based on your connection. Oh, that's interesting, Hunter. 20 points. Thank you for that right there. So, which is probably a good setting for a lot of people because maybe the internet might fluctuate, and that way you can, hopefully we'll try to keep you live. Okay. So, once again, huge shout out to Dave Ramsey because it really comes down to every dollar. And so my advice to people is think about how long you're in college. Think about how long you're in college. You're in college for 4 years mostly. If during college you make an effort to save $3 a day, you literally are doing the mathematics. 4 times 3 times 365. And there's like another day in there because there will be a leap year with 4 years. So with this effort right here alone, just $3 a day, you're saving that much money. Now, you might say, well, that's not a ton. It's something. It's a good amount. And you could use that to help pay off your student loans. You could put that towards a car. But I would say $3 a day is not going to be a dramatic change to your life. So here's Brian's life advice. Itemize what you're doing right now. Say, okay, right now I, buy a coffee a day. I go to McDonald's and I buy this, or just think about what you do. And then figure out like, how could I figure out a way to still live and enjoy what I'm doing in life and to maybe just lower how much I spend each day? Like maybe start journaling, tracking it, look at the variation in it. And we oftentimes focus on like big expenses, like, oh, I can't buy this car or I can't buy this TV. But it all comes down to the little expenses that we do every day. Like every day, homemade coffee right there. Like I've got, my favorite thing is I've got a pour over thing. Zone. It's one of those pour over coffee makers. I'll show you what it looks like on here and then we'll get serious here again in 10 seconds. But I've got a pour over coffee maker. It looks like this basically, where you pour your hot water into here and then the coffee drains down to here and you get the coffee. And so it's like one of the best drawings I've ever done right there. And so this coffee maker I really like, makes really good strong coffee. And I really enjoy it. And so, yep, Keurig, all these things, reusable K-Cups. There we go. Camden giving some great advice. Just, once again, you don't have to, like, change your life completely. Claire, that's too funny. You could do it for a special occasion, Claire. You could do it for a special occasion, Claire. So you could say, like, okay, I really like doing this. I really like buying hats for my cat. And so I'm going to do it on these holidays. And it's going to be more fun. Like I'm going to, and you can always just kind of window shop for them. And so, if someone comes back to me like 4 years from now and they say, Brian, I saved up this much money because one day you told me, I wish I'd given myself this advice. The advice I give people is advice I try to follow. Like the reason because I make my coffee in such a way that I like it. And to me, it's pretty comparable to Starbucks. Now, you will every once in a while see me use my refillable Starbucks cup because I've got a refillable Starbucks cup and it costs like $1 to refill. So that is $1. It's way down from the $3 I used to spend at Starbucks. But, I'll be on campus. I'm like, oh, I really need some coffee. but I probably do that like 3 or 4 times a semester. You're like, I see you there every day, Brian. I know your secret. No, I've lowered that. So I really enjoy drinking my own coffee. I try to make it at home when I can, fill that up and bring it with me. So once again, look at the variation in the data, figure out what works for you. Dunkin's better than Starbucks. Or maybe you say, I really like Dunkin', but I own a Keurig machine. So on the weekend, I get to treat myself to Dunkin'. That's my treat. On the weekend, I get to treat myself to Dunkin'. And so maybe you do that. Like however you live a life that you love and do that. I know. Man, I've had some favorite, like Jimmy Astro Lewis. No one knows him anymore. Jimmy Astro Lewis, he's my man. So good stuff right there. So look at what you're doing in your life. Try to figure out a way to save like even $1 a day. No joke. $1 a day. $1 a day is $365 in a year over the course of your college career. You know what? Who would like to get $1,000 when they graduate college? Just start putting it, like start thinking about this. Be like, every day, if I do this, I'm going to put like $1,000 away. All you need to figure out is how to save $1 a day. You save $10 a day, boom, you got that. You save $20 a day, boom, you got this. If you're eating out a lot or stuff like this, not trying to ruin the economy, but if you save $20 a day, you'll have $30,000 by the time you graduate college. So it's a lot of money. So, but, don't like destroy your life and be like, I'm not going to ever do anything. Every paycheck you get, put $20 away. That'll do it. I'll do it. Let's do this. You guys ready? Let's talk about confidence intervals really quick because this is going to lead into today's lecture. Brian's life advice is over. But once again, I just want to say one more thing on it. To make changes in your life, you have to think long term. You can't say today's the day that I start saving a little bit more money. Or you don't say today's the day I'm going to save all my money. You make the changes long term. You say, okay, I'm going to try to save $3 a day. What? Oh, that's awesome. Well, don't worry more. Don't worry. Congrats. I bet they wish they were at the end too. I bet they were like, oh, I wish I was finishing college too. The new stuff today won't be on the exam. But what we need to know, and congratulations, Morgan. Let's get done. Let's get graduated. But you know what? Now you get a job and start putting a little bit away. Say, okay, now I'm going to have a job. I'm going to focus in on that. I'm going to focus in on my career, on my marriage, on whatever you want, and start, like building up and saving. So thank you, everyone. Everyone throw some credit. People are already doing it, but keep doing it if you want, because that really means a lot. It's a big, big accomplishment. Like when I graduated college, I was like, oh, it's over. I did it. I'm done. So, congratulations to all the grads and especially in this crazy time. What do we have right here? We have here P hat. What does this mean? We're back to reviewing a little bit now. 10 minutes of Brian's life advice is over. What is P hat, though? Sample proportion, you guys are right. 20 points, Sarah and Jared right there. P hat is sample proportion. Z is a z-score. Z is a z-score. P hat, sample proportion. If P hat is 0.8, what is Q hat? 20 points first person is P hat is 0.8, what is Q hat? If P hat is 0.8, what is Q hat? This time it looks like a Q, not an E. It's 0.2, you got it. Taylor, William, and Sarah, and Keaton, you got it. And so Q hat is the complement of P hat. We understand what it is. Complement with an E. Josh, right there. You're right. 20 points, Josh. And so we've got here N, which is sample size. So does everyone see how this all works right here? Oh, don't worry, Camden, 20 points. Don't worry. I see all the chat, and I like it. 0.8, not 0.08. 0.08 would be 0.92 complement. Mm-hmm. So right here is a confidence interval. And when you make a confidence interval, we didn't write this yesterday, so this is slightly important for the test. A confidence interval would be interpreted. It's just you don't write these out anymore. The homework is a good review over it. I am blank % confident that the true blank. I'll tell you 1 second, Jared. Is contained in the interval. Good question, Jared, 20 points, because the answer is this whole thing solves out to a what? This equation solves out to a what? What does the whole equation solve out to? This whole equation has a plus or minus, which has a margin of error. This is a good start to today's lecture, basically. Well, that's the margin of error. It solves out to a confidence interval. You're right. So it solves out to an interval. And the interval has a center plus or minus a margin of error. If our interval is made from a sample proportion, what are we trying to estimate? If our interval is made from a sample proportion, what are we trying to estimate? If our interval is made from a sample proportion, we are trying to estimate the what? And we're always trying to estimate the something for a something, the parameter for a what. If our interval is made from a sample proportion, I'll take that right, Thomas, 20 points, Thomas, the population proportion, the actual, the truth. There's a lot of ways to say it, like actual works. So if you just want to say the actual proportion of people who blah, 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 that would be correct. Great job, Thomas, right there. The actual, the truth for the population proportion, which is a parameter. So all parameters are for a population. There's a lot of synonymous words here. Like you could say the population proportion, which is the parameter. So all these P's, all these alliterations, but proportion does not always mean population because you could say the sample proportion. So what do we have right here? Watch this. Here's today's lecture, which is not on the test. Part of today's lecture. Please take a look at this interval down below. What is the center of this interval right here? What is the center of this interval? That's subscript. What is the center of that interval? Y bar, which is the mean of Y, the sample mean. 20 points, Jared, Devin, and Thomas, all those answers right there. You're totally right. It is the sample mean of variable Y, technically. I mean, like, sample mean's fine. I just say sample mean usually. But technically, the sample mean of variable Y. So when you look at this right here, what is this interval trying to estimate? 100 points. First person who tells me this interval from the sample mean is trying to estimate the what? Who knows? Sarah and Jack and Cooper, 20 points. Who's going to get the 100? It's trying to estimate what? This one right here was the sample proportion trying to estimate the true proportion. This one down here is the sample mean being used to estimate the what? No one said it yet. We need the full thing. You're kind of right. I'll take it right there. Maya and Alyssa right there, 100 points. You're right. They both said true mean and population mean. First people to answer those right there. You are correct. 100 points. Tough question. But take note, I try to raise the points when I want you to really know something. Now listen to this. Ready? The top interval is being made from the sample proportion to estimate the true proportion. The bottom interval, 20 points, everyone giving that answer, just making sure you know it. The bottom interval is from the sample mean trying to estimate the true mean. Or you can say population, which is fine too. But does everyone notice we use a sample to estimate the truth? So it's very important to see this structure, that we have the sample proportion trying to estimate the true proportion, the sample mean trying to estimate the true mean. Like imagine if you had somebody running a mile. If you had someone running a mile, would you use interval 1 or interval 2 to see how fast they truly run a mile? Like you take a bunch of samples, you watch them run a mile. Would you use interval 1 or interval 2? It's a decent test question. You'd use interval 2 because it's quantitative. Because it would be on average how fast do they run the mile. So you're trying to figure out their true mean mile time. Let's say you want to know how many students have a... I'm obviously switching. You don't answer right now. You want to see how many students or what percent of students have a pet at home. Like, would you use interval 1 or interval 2? And if you're doing the percent of students who have a pet at home, you'd be asking the true proportion of students who have a pet at home, and it'd be interval 1. So now I got to figure out. I'm going to offer 100 points. So you have to put this. You have to do something like this. You have to come up with a new one here. And you have to say, like, 1, proportion. Every class, we got to mention Taco Bell. You have to do something like that. But I'd actually prefer you do it for interval 2, because you can just say proportion of people who this for interval 1, which is true. You could always do that. So can anyone come up with one for 100 points? I might pick a few out here for interval 1 or interval 2. And this is a really good kind of review of confidence intervals and a segue into a lot of what we're going to talk today. So it's a review of what's on the test with the top one, but then, oh man, Thomas, I am jealous. Thank you, Michael, right there. The proportion of students, Michael gets 100 points right there. The proportion of students who like 201. You can get up to 200 points today. The limit is 200. I'm going a little crazy. I might not up it. The limit's 200 today. Everyone hear that? Limit 200. So, does anyone have another one? Another one. Another one. Thank you, Nicole. Proportion of students that go to class? Yeah. That, especially for online classes. Kate, that's a really good one because you might want to know, and you see, you'd have to be careful. You might have to stratify because you would acknowledge a difference between online classes and in-person classes. Everyone see how that would be stratified? So you would say, let's go take cluster samples of classes, and each class is a cluster because you would look at each class and see how many people go to each class. And then, I don't know what that means, Neelan. And then you would make sure you have enough online classes, enough in-class students, because those are the strata. The strata, review for the test, is online versus in-class, and then the clusters are each class. Proportion of people who have eaten at Brent's Pizza, yep. Does anyone have a toot? Oh, here we go. Morgan. And so Alyssa and Morgan, let me read Morgan's. True mean of how fast a person can run 2 miles. Well, there you go. Yep. That would be right there. True mean of how fast a car can complete a lap. Yep. Because that's the on-time average. Matthew, great job. If you put something I didn't acknowledge it, you still get 100 points. So Jared and Keaton, you get the hundreds right there. Good shot at it. I think everyone put something pretty correct. But this is for proportions right here. So this will find the true proportion. The top one will. The bottom one will attempt to find the true mean. And it's not gonna find it. It makes an interval to estimate. And how do we interpret it? Let's see what Sarah said. True mean of how fast someone can run to the hill. Yeah. Like, or we'd say from the ag campus. Or yeah, think about that. That's a good question. I like that a lot, Sarah, because think about this. We could ask, how long does it take for students to travel from the hill to the ag campus? Now, we might have to stratify based on if people take the T or if they walk it. So now we might have to say, okay, well, we know 70% of students walk it and 30% of students take the T. So now we got to make sure in our sample of 100 students, we take 70 students who walk and 30 students who take the T, and then they record their time. So you'd have to stratify based on the different ways people travel to ag campus to best understand and estimate the true average time it takes for people to travel from the hill to ag campus. Does that make sense how we're putting in stratified into how we would collect our data? I love walking from the hill to ag, but I get to visit someone special when I would do that. I would say hill to ag takes about 20. It takes about 20 because Haslam to ag, it takes 15. And Haslam to hill is pretty close. I mean, it's right next door. You see, I mean, it's a nice straight path. So, true mean of how long it takes for someone to finish a lap on Toad's Turnpike. Yes, Toad's Turnpike is classic. 100 points right there. Yep. And so this is very important for us to understand when we would interpret this. Here's how it would be interpreted. We're going to make up an interval. Oh, I didn't. Sorry, I went too quick and I forgot to do that. So when we interpret this today, and I want to do this way because, so to clarify for the exam, we don't need to know how to calculate. You do. You will know how to calculate this interval, but this is on exam 3. Exam 2, exam 3. Once again, exam 2, exam 3 down here. But so intervals are going to be very important. So if you don't know it for this exam, not the end of the world. If you don't know it for the next exam, pretty bad. Okay, so here's the kind of the okay. So these z-scores will be given. Z-scores will be given. And so this is just interpretation right here. UT claims that it is okay to have a 15-minute break. Wait, we just said travel. UT claims that the 15-minute break between Hill to Ag Campus is okay for most students to have to travel between hill and ag. What would you believe about their claim? Or would you say that's a good claim? And why? Why are you saying it's false? 20 Ports Morgan right there. You're right. Why are you saying that's false? Why? Just read your interval. Read your interval, and let's highlight the words that have changed in here. I think people are saying it. It's outside the interval. And so you would say the average student takes way longer than that. I'm 95% confident it takes on average between 25 to 28 minutes to travel between the hill to ag campus. So you can literally say it in the I am 95% confident. The true mean time it takes for someone to travel between hill to ag campus is contained in the interval 25 to 28 minutes. It is. I'd have to see that. I've taken the T a few times, but not that much. Why is it outside the interval? It's just a claim they're making. They could make any claim. They could say it only takes you 5 minutes. So you would say, I don't believe their claim because the data goes against it. So is there a way to know? Well, here's the thing. Think about this. Do you know how long it takes on average for all students to go from hill to ag campus? Like every single student, would you ever really be able to know the truth for how long it takes the average student? Like, is that something we could probably understand or something we have to estimate? What do you think? We would understand or estimate. I think Sarah's on track. That is something we'd probably have to what? And this is why we use statistics, is because statistics are estimates. We would never really understand how long it takes. Like, you can't say, we took all students. Well, then there's variation within each student. So you can't say, I took all the students, I had them all collect data. It's like, well, there's variation in how much time they take. Every student doesn't take the same amount of time each time. So even if you had every student walk from hill to ag campus, you'd have a really good sample of how long it takes on average for all students to walk from hill to ag campus. So I'm 95% confident. You got it. Alyssa, 100 points right there. Amazing work. So this is what we need to know of what the interval is doing. The interval is trying to estimate how long it takes for all students to walk from hill to ag campus, like the truth. Like we're trying to tell you, T, well, for all students, this is how long it takes on average. We think, and think about what suggestions we could make as people who do analytics. We could say to people on the ag campus, and I think this is a good suggestion, I would say it personally, and I'll say it too. If a student tells me that they are walking from the ag campus to the main campus, and they might be late, I always make an exception. So whenever a student says, I'm traveling from the ag campus to Haslam, and they say, I might be 5 to 10 minutes late, I say, no worries. I say, I'll make sure I help you out with any time you need or anything like that. So I think this is a suggestion we make from the data when we can show the data says 15 minutes is not usually going to be enough time. So think about how we use data to make decisions. And this interval right here tells me that most students, the average student, will not have enough time because the average student takes 25 to 28 minutes. How many of these types of questions are on the test? Usually it's more like my Pearson right now, especially with the new online tests. It's more identifying the correct interpretation. So great question right there, Claire. You won't have to write them out. I think they're easier now because it's more like my Pearson where you have to identify the right interpretation. But we might switch it. That's very wrong. Because can anyone tell me what the sample mean was? This is also another question. So this is wrong interpretation for this reason. I'm going to put this in red. This is incorrect right now. That it shouldn't say sample mean. Can anyone tell me what the sample mean was? What was the sample mean? These are really good questions right here. This is yesterday's lecture and today's lecture and really good questions related to it. It is Y bar, but what was Y bar? Kyle, 100 points. You are on track. You got it. The sample mean was Y bar, but what was it in this problem? How could we figure out Y bar? That's actually the claimed. That would actually be mu naught, which we haven't talked about that yet. Don't worry. Don't worry about that one. Pretend Brian never said that. 200 points first person to tell me Y bar. And when you see it, you'll be like, oh, you'll be like, no way. I'm going to max someone out. And when you see it, you'll be like, that was obvious. 26, Kyle, yes. Look at all those, I love all those exclamations. Kyle's like, I know it. It is this. What did Kyle do to the interval? Think about this. The interval down here is y bar plus or minus a margin of error. Another quick 200 points. What's the margin of error on this interval? We've given test questions like this, and people are like, how do I figure out the margin of error? And we're like, we can't tell you. 200, boom, William, 200 points right there. You got it. Everyone else, 20 points. Everyone who answered those questions or repeated the answers, 20 points. You're following along. So this right here, when this interval solves mathematically, it solves out to 26 plus or minus 2. And you're actually learning, you find the mean of the interval. Nice job, Maya, right there. The mean of the interval is the center of the interval. So does everyone see if you average these two numbers together? So let's write some real quick formulas on here. The center of the interval. Here, let's draw this. Then we're going to kind of hop to lecture here. This is really good stuff right here. Okay. So you have here the center of the interval, the upper of the interval, the lower of the interval. And you can make up fake numbers to help you out. We could say, okay, we're going to go get a steak dinner. A steak dinner usually costs about $25. And it could be as much as 30 or it could be as much as 20. How could we write out, how could we find the center of this interval if we didn't know the center? Just go ahead and think about this. If you didn't know the center of the interval, you can probably kind of just see it as you're thinking it. But if you didn't know the center of the interval, how could you find the center of the interval? 100 points first person. And I'll take that, Hannah. You know it. You got it. So you're right. I think you're seeing it. I think you're seeing it, Morgan. Yep. Oh, be careful. Not times though. Plus. So you got it right there. And you got to find the mean of 20 and 30. That's it. People are seeing it. If you see it, it's like, oh, it's just. So the center of the interval is equal to upper plus lower divided by 2. Now I want you to think about this. I want someone to just put in words. Like, tell me in words what the margin of error is. It's what of the interval. The margin of error is what of the interval. The margin of error is what of the interval. The margin of error is what of the interval. People see the answer. You guys got it. 20 points, all those answers. What is the margin of error, though? What is it related to the whole interval? It's the plus or minus. People are doing some really good answers right now. It's what the length of the interval, though. Let me say it that way. It's what the length of the interval. That's what I'm looking for. The margin of error is blank the length of the interval. Someone's going to say, right as I said, I bet, half the length of the interval. The margin of error is half the length of needy right there, 100 points. Half the length of the interval. The margin of error is half the length. We should have that definition in our mind right now, that the margin of error is half the length of the interval. So what do we need to do? Mathematically, we need to find the length of the interval. The length of the interval is the upper minus the lower. And then if we want half the length, we divide by 2. Does everyone see what we just literally said? It's half the length of the interval. So this formula right here is half the length of the interval, is the margin of error. And then you can see if you solve it, it'll solve to 5. So I often ask people to think of little small questions like this is minus 5, and this is plus 5, and this formula could be written 25 plus or minus 5. So the margin of error is half the length of the interval. So understanding little questions like this will help you understand the confidence interval every time. Always do the steak dinner question. Like, it'd be like, a steak dinner could cost $30 to $40. Well, let's do this. A steak dinner could cost $30 to $70, depending on where you go. 30 to 70, a good steak dinner, like a good filet, a 10-ounce filet. Now, I know there's ones outside of that, but still. $30 to $70. What is the, can someone give me the full interval? You have to give me the full interval with the plus or minus. $30 to $70. Give me the full interval for 100 points. Full interval, who's got it? You have to be like this, plus or minus this. 30 to 70. What's the full interval? Boom, Morgan right there, 100 points. Morgan's, yep. 20 points for everyone else. Isaac and Michael. Morgan said the full interval right there. Yes, and Needy, 20 points. Morgan was first. Great job, and you're seeing it. If you're able to do these questions, you're able to figure it out. And you can kind of do it in your head. Like, probably a lot of people are, wait a minute, 30 to 70, 50, plus or minus 20. You kind of do it really quickly. Plus, if you know the center, another formula for margin of error, space pen's coming back. Another formula for margin of error, 100 points. Who can write another formula for margin of error? Here's your 2 hints for formulas for margin of error. Who can write another formula for margin of error? Because you never know what's going to appear on the test. Who can give me, first 2 people to give me 2 other formulas for margin of error. 2 other formulas. 100 points, first 2 people. Upper minus center, yep. Upper minus center is a margin of error. And also, someone's going to come up with a weird, yep, center minus low, Alyssa right there. You got it. And that was also Laura and Alyssa, you got it. You're seeing it. You're understanding how this works. Does this make... I'll take that, Ethan. Ethan, I'll take that for 100 points. Ethan said 2 times the margin of error is the length of the interval. You're right. Do you guys feel right now that confidence intervals make a little bit more sense? And then we've got it here, square, yep, p times q over n square root is the formula we use when we're doing, and then we times it by z. You're right. Nice job right there. That is this margin of error, but there'll be different margin of errors depending on which intervals we do. So the interval we did yesterday has a margin of error with this. Last 100-point question. We're going to go to the notes here. In the interval we did yesterday, what gives us the confidence level? In the interval we did yesterday, what gives us the confidence level? In the interval we did yesterday, what gives us, for 100 points, what gives us the confidence level with the interval we did yesterday? The confidence level is given by the what? The confidence level. The confidence level. The confidence level is given by the... I tricked everybody. 200-point question, first person. Z-score, Michael. Nice job at the Z-score. The Z-score, today, the confidence level will be given by the T-score. And this goes to the very end of yesterday's lecture with the precision and the confidence. So all these important things right here. Can you explain the difference of P and P hat? Yeah, okay. Good question. So this interval right here is an interval made from P hat to estimate P. P is the true proportion, where P hat is the sample proportion. Like, this is the true proportion of students who like Taco Bell. Like, if we could talk to every student and ask them, do they like Taco Bell? Maybe 60% of them like Taco Bell. This is when we talk to a sample of students, and you could say 60 again. You could say 60 out of 100 students like. So this P hat will always have a sample size. P is the truth for every single person in the population. Like, if you somehow knew it. And in some instances you do. Like, maybe Ford knows maybe 4% of Ford cars have some defect and can't be sold. Like, we literally can't sell them. So we don't sell them. So we know, Ford knows what percent of its cars it doesn't sell. It would know that information. So in some instances, and this would go to sampling distributions of the sample mean, or proportion, excuse me, the other thing's today's lecture. If Ford were to know 4% of its cars it does not sell due to some defect, it knows, then it could ask, which was a part of yesterday's lecture, if we were to have 1,000 cars, what would we expect to see for the amount of cars we can't sell out of 1,000? So in that instance, they know the truth and they're going to the sample. But with a confidence interval, you only know the sample and you try to estimate the truth. So maybe another newly started car company wants to see, like Tesla or something, wants to estimate what percent of its cars are defective. So they take a sample of 1,000 cars and they test them to see if they're defective to estimate the true proportion of cars that are defective. So it changes slightly when you go either from the sample to the truth or the truth to the sample. And the same thing holds true. This is kind of going into today's lecture also, because up here we have mu, because the sample mean is used to estimate the true mean. But there's instances where we might know the true mean when we could use it to talk about the sample mean. So guess what? It's time. It is time. Confidence intervals for the mean. Central limit theorem. It's not too much. I think yesterday's review was pretty good for it. And if you did the homework, if you understood the homework in the quiz, I think you'll do fine on the questions on the test. Just read them carefully. Follow the simulations carefully. Remember, the homeworks and the quizzes you get multiple attempts on, but I do think they're good practice. Good question right there, Sarah. I do think the homework and quizzes are good practice. You just get more attempts on them. So just remember, when you take the test, you get like that one attempt. So if it took, and I don't mean to scare anybody, but if it took you like all 8 or 9 attempts to get a good grade on the randomness, and you're like, ooh, I got those because I guessed. Well, on the test, you get 1 attempt. So if you're doing all the homeworks and quizzes and getting them all right on the first attempt, that's a really good sign. If you struggle on some of them, those are the ones you need to practice. But once again, if the test goes poorly and you get like a 50 and you've been doing everything, you at least still have a 75. So do all the homework, do all the quizzes, and no matter what, it'd be really hard to make lower than a C. There is a randomness review video. Yep, there's a chapter review video. And so go to the page. There's lots and lots of review videos. If you can't find them, email me immediately and I'll send them to you as quickly as possible. Don't start the exam later than 5 tonight, I'd say, though. If it says round up to the nearest integer, if my answer is yeah, yep, you'd round up to that. You got it. Don't be, I've only seen a few grades. And once again, it's bimodal. It's very bimodal. It's very bimodal. But once again, if you make like a 60, 70, like if you make a 70, that's not that bad. You've got an 85 average. So if you finish your test and it says 70, be like 85. That is if you've been doing all the work, all the quizzes. So once again, don't forget to do the quizzes. I'm just like, if I can beg you to do one thing, it's please do the quizzes. Because if you're not doing the quizzes, then I don't think you'll understand the rest of the material for the rest of the semester. And if for some reason it's not clicking, you still have your quiz grades to help you out. Super necessary. I agree. Kyle, 20 points right there. Thank you, Kyle. I think it was like 44, 40, something like that. 40-ish questions. There's no practice. Sorry about that. I'll try to make more. I've been working on the project and everything. Sorry, Keaton. I know we need more practice stuff. I'm sorry. It's sorry. I think that my Pearsons are decent practice. Like they're similar-esque. Still due tonight. Still due tonight. Because we're keeping to like 1 assignment due a night. I know it's a lot. There's a lot. I would stay after class. I would do it. So I know it's a lot. Don't miss the quiz tonight because that'll start you off on the wrong foot for the next test. I know it's a lot, guys. I know. We got this. You ready? We got this. We just think we're going to knock out the quiz, we're going to knock out the test, and we're going to be done for like most of the material. Then we'll just have one more thing to do tomorrow. Let's do this. Ready? Here we go. Let's talk about the central limit theorem. The central limit theorems. I can't reopen the quizzes. The homeworks. So, because the quizzes they're closed. The quizzes, they're closed, but the homeworks are good practice. The central limit theorem. So, previously, yesterday, we were talking about proportion data. And we did the following. We knew yesterday that the true proportion was like 4% of Ford's cars are defective. So then this asks, I'm going to highlight a word right here. I need some people to help me out. What would we to see if we took a what? What E word did I use for the mean? It's the mean for the sample proportion. But I said, what would we, E word, expect to see, Isaac, 20 points right there, expect to see if we took a sample proportion? And what would we expect to see? A true proportion. Well, guess what? You'll see it in the slides here in a moment. But you know what we can do? What if we knew the true mean? Well, guess what? Look at how similar this formula looks right here. This formula is basically identical to the one I just wrote, because now, what would I expect to see in a sample mean? I'd expect to see the true mean. Do you see how, once again, we're just saying, it's like saying this. The average American is 5'8". What would I expect to see if I took a sample of Americans? I'd expect to see 5'8". And when I say the average American is 5'8", that's what I'm telling you. Then when I say, what would I expect to see if I took a sample on average? Well, this is what I would expect to see for a sample mean of Americans. Because I know that the mean for Americans is this. So if I took a sample mean, which is this, I would expect to see the mean. Does everyone follow the words as I say this one more time? I know that Americans are on average 5'8". Well, I would expect to see in a sample of Americans the average to be 5'8". That's what I expect to see. So we understand the easy part of this. There's a little bit more difficult part to it, which deals with the central limit theorem. Now, one of the best visualizations we have, I'm going to hop over to the main screen. Like, we just left the main screen. I know, but we got to go back to it. So one of the things I showed my brother, and he's like, whoa, this is so cool. It makes sense to me now. Okay, so here is the central limit theorem applet, and it shows you what's going on with it. So what we have here is normally distributed data. We know that the average American can do 16 push-ups. So apparently we know this. I'm just making that up. You're like, how do you know that? Well, I'm just making it up. So the question says, we know the average American can do 16 push-ups. If I took a sample of 5 Americans, see how this is going to be the mean for 5 Americans. If I took a sample of 5 Americans, how many push-ups would you expect them to do on average? Who can answer this for 100 points? If I took a sample of 5 Americans, what would you expect the mean of their push-ups to be? 16? Kate, 100 points. You got it. Same question from before. You literally just solved the formula that we put in the slides right here. You solved this formula. I said this is the truth. Well, then you told me this is what I would expect to see in a sample. So watch. Here's one sample of 5 Americans. You see each American, like that American, whoa, that American did like 20 push-ups. They didn't do as many. They did like 8. And actually we got 11. Let's do another sample of 5 Americans. Now this blue dot down here is the mean for these 5 individuals. Does everyone understand what's happening? I'm going to watch 5 Americans. Okay, that one did like 14, 10, 11. Oh, no. That American did like 3 push-ups. And then we average together and get the mean for those 5 observations. Like this one will be right about there. Yeah, because you average them together, and that's the blue dot. So every blue dot down here is the mean for 5 black dots. Does that make sense? And what happens if I were to repeat this process? Like I keep hitting animate, but I can click 5 and it does it 5 times for me. I can hit 10,000 and it does it 10,000 times. So now I've done this over 100,000 times. I can just keep doing this. And what do you notice the mean of this distribution is? Wait a minute. The mean of the distribution is the same mean. And it's normal. Interesting. Interesting. And since it's normal, we can use z-scores. That's even better because we know how z-scores work. So why do you do it more times? It's a simulation. It's a simulation to show you. So increasing the trials review for tonight's test. Increasing the trials makes so 100 points, Kate. Great question right there. It's got a, oh, you said I'll still give it. I thought you said, why do you do it more times still? But when you do it more times, it makes the simulation more accurate and gives us a better representation. So, and Kyle points out, it's normally distributed, Kyle, 100 points right there, with a mean of 16 and a standard deviation of 2.24. Good notation, Kyle. And so when we look at this right here, what if it was skewed, though? What do you think the mean of this bottom distribution will be? If I do this repeatedly, who for 100 points can tell me what the mean of this bottom distribution will be? And you're right, Thomas, as we do more simulations, that's the law of large numbers with more trials. Thomas, 100 points, amazing notes. That is the law of large numbers showing us that with more trials, we get a more accurate representation. 100 points, Thomas, Josh, and Sarah, and Chai Chuna. Please, if I'm wrong, please correct me. And continuing on, what do you notice right here? What do you notice right there? But tell me, does this look normal or does it look skewed? Does that look normal or skewed? Looks a little skewed to me. But watch this. What if the sample size was 25? Now, why is it less skewed? The central limit theorem. Now, every blue dot down here will be the average of 25 black dots. So that one blue dot right there is the average of 25 black dots. So to get one observation in the distribution of means, we have to have 25 black dots, like 25 individual observations. And what are we going to do to these 25 individual observations? We're going to average them. Now, if I were to get a black dot right here, think about what would have to occur. We'd have to get a whole bunch of observations over here, basically, because any observation down here will average with it. So it'd be really odd. Like there's one observation, there's another one. But on average, we're usually going to get something that averages out. That's why you usually see when you do this that the mean of all this is going to go towards this. You know, this is a bit weird right now, but then we do the simulation a lot more. It goes towards it. And wait a minute. This looks very, very what now? Not perfectly, but it looks a good bit more what now? It looks more and more what? Normal. That's weird. It's almost like when the sample size is small, it's skewed. And as we increase the sample size, it starts to get more normal. And another thing, like two things. Who can write the two things for 200 points in the chat that happen as we increase the sample size? The distribution here is small, so that doesn't look normal and it's really spread out. And then it's becoming more normal and it's getting tighter. What two things is happening as we increase the sample size? Hannah is right. Hannah, 100 points right there, but I went to two things. We'll see who says it. People are basically getting it. Basically. I'm going to give everyone 100 points. Why not? Everyone's basically on track. Here's the two things. So I'm going to state it explicitly now. As the sample size increases, I'm going to say three things, but I'm going to give the two major things. As the sample size increases, the distribution will become more normal. So here's 2, and then here's 25, and it becomes more normal. Thing number one becomes more normal, and so normal is also symmetric. So it's more normal, like unimodal symmetric, more normal. And as the mean increase, or as the sample size increases, so as we increase the sample size, it also becomes tighter. More normal and tighter. Now, a lot of people were pointing out a thing that the mean stays the same. That is true. The mean does not change, which is a good note. The mean does not change. Look at the formula we just wrote a moment ago. The formula we wrote a moment ago has nothing to do with sample size. The mean is always the mean. Well, the mean for the sampling distribution of the sample mean is equal to the mean. The mean does not change. As sample size increases, it becomes more normal and tighter, and the mean does not change. Zula, 100 points right there. Amazing note. That's exactly everything that you would need to know. Is that as the sample size increases, it becomes more normal. So it's going to go from a skewed to a normal. And it becomes tighter. Goes tighter. And the mean does not change. So that's some big notes right there. That's a big thing to know. So we call this the central limit theorem. And it's done from all possible averages. And that's what you were visualizing just a moment ago right here. We were visualizing when we did this, we created a distribution of all possible averages. And we can show it via simulation. Now, we can't literally do all possible averages, but if you notice, this simulation now has 3.4 million trials in it, and nothing's changing. It's like so decimal place accurate at this point that it's like, okay, that's the answer. And it shows it works via simulation. And they've done mathematical proofs on it also. Now, the weird thing is this standard deviation. The standard deviation, there's got to be a way to figure it out, right? Watch this. I can figure it out very quickly. I'm going to find 1.25 if I take 6.22 and divide it by 5. Oh, there it is. Oh, so it should go to 1.24. Let's see. Are you going to do it? It's so close. Wow. I really wanted to say 1.24. Like, I want to keep going until it says 1.24. I'm going to keep simulating because it should go to 1.24. It's so close, I bet. Oh, no, really? Don't, simulation, don't fail me now. This ruined my day. It's like a video game. Why did I divide by... Does anyone have any idea why I divided by 5? The answer is here. You'll see it in the formula in a second. I'm going to keep clicking until anyone... I know, simulation failed. I wonder if they're not carrying enough decimals in the background or something, or if I broke the simulation. Oh, you see the skew size change. That's cool. Does anyone know why I divided by 5? Okay. I think I lost the game. It's like 35 million simulations, or 335 million or something. We'll start over. Watch this. 1.25, you haunt... There, it said it for a moment. See, now it says 1.24, and it's sticking to it. It's so close. It's so close on the last decimal. I saw it too, I know, and it's like going between... We're going to stop on it. Really? I wonder if it's somehow with the way they're doing the simulation, because they keep going to 125, and I'd really like to know in the background... This apple's going to make me very mad. Or I want to look into the central limit theorem even more. Because simulations are meant to model reality, and it's off by like a tiny decimal, and that gets me. It's Hannah. 200 points, Hannah. Hannah, while we were doing the simulation, we were freaking out. Hannah was doing it. Hannah was figuring out the formula. Right here. Hannah, amazing work. You got it. There was a 25 for the sample size. And so it was literally just dividing by square root of 25. You got it. Nice work. Let's hop back to the notes right here. Sorry, I just spent like a minute of class clicking a simulation. If simulations don't do what I expect them to do, I'm mad. So right here, you'll notice that this is the standard deviation of y bar. This is the standard deviation of p hat, which is yesterday, p times q over n square root. I do agree, Neelan. Totally worth it. 20 points, Neelan, right there. It was, thank you, Alyssa. And down here on the bottom, we have n, which is the original standard deviation of the square root of n. Please make sure you know this notation, that we have the original standard deviation right here over the square root of the sample size. Now, why is this one using this formula and why is this one using this formula? It's almost like one of these is for what kind of data? Now, I wouldn't write this on the test, but it's almost like this is for that. And literally going back to the first lecture, mean versus proportion, Nicole, 20 points right there. And so it's categorical versus quantitative. So you've got two different types of questions right here. One is categorical, one is quantitative. So there's a different formula for which one you use. So if you're asking like, what proportion of our cars are defective, you would use this. But then if you said, what is the top speed of our cars, you would use this, because top speed is quantitative. So you have to use the right one. So conditions, we skipped them, but guess what? And that's just showing you the simulation. Condition 1. Who knows condition 1? You know what's going to happen here. You know. Someone's going to say it. Random. Condition 1 is random. Condition 1 is we randomly select the observations. Condition 2 is less than 10% of the whole population is sampled. We can't sample more than 10%. Say it for me. Say it. Say it. You gotta say it. I need to know what to do next. I gotta do something. I mean, I'm doing it right now, but pause. Stop. Slow your mind. It's not a condition, but we just slow down. Remind me of that, Joseph. We stop. And we ask ourselves, is it quantitative or is it categorical? Stop right here. Stop. 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 Pause. And this one's quantitative, so we use the large enough. Because, gotta hop back to the screen. If our sample size is not large enough, the distribution will not be what? If our sample size is not large enough, why do we do all these conditions? 200 points first person. This is so important. Why do we do the conditions? Zulon, amazing work. Exactly. If it's not large enough, it's not normal, which is one of the things the central limit theorem does, is as the sample size increases, the distribution of the sample mean becomes more normal. Now, this isn't the original distribution. It's the distribution of the average of two observations. And so you can see it appearing down here, each one of these, a theoretical distribution of averages. And then as we do it more and more and more times and look at the theoretical thing, and this is theoretical, it's like all samples of size 2, what would occur when we average them together, it will become more normal as we go to larger sample sizes. Where you at? So now it's normal enough. We can do the normal methods on it. It depends. Like, think about this. So let me ask this question. Here's a tougher test question. We're on test 3 material right now. Let me switch back. Ford wants to figure out the miles per gallon their cars get. You got it, Josh. I'll do it after this. You got it. Ford wants to figure out the miles per gallon their cars get. Ford knows from they don't want to figure it out. Ford knows from historical data that their cars get on average 25 miles per gallon for a specific car. It's a very right-skewed distribution with a standard deviation of 5. So immediately should write down right here, 25 is the mean and 5 is the standard deviation. But I did say it was very right skew. They take 100 cars and they want to see what would happen in 100 cars. Like they're seeing what would happen in these 100 cars. So they know the mean. They know the standard deviation, which is important for the formulas right here. They know the mean, and they also know the standard deviation. So when I say they know the standard deviation, I'm giving you this. And when I say they know the mean, I'm giving you this. And now you should be solving for this, which is the thing I just gave you. And you should be solving for this. And they take 100 cars. And I picked 100 for a reason. First off, what are the new mean and the new standard deviation for the sample of 100 cars? Who can tell us in the chat, 200 points, what are the new mean and the new standard deviation for the sample of 100 cars? Remember, n is equal to 100 here. So this was the original mean. This was the original standard deviation. And n is equal to 100. And I picked 100 for a reason. So you've been following along. You should be like, okay, wait a minute. The mean is equal to, you got it right there, Josh. Josh, 200 points. Be careful. Maybe I reversed my words. People are saying the mean is equal to the mean. The mean won't be 20. What is the mean equal to? Did I say 20? Did I miss? Everyone's putting 20 in the chat. Look at what I've written, because maybe I misspoke. So it's 25. Because do you see where I've written mu? So mu is, this is what, so to be very specific, in a problem you'll be given this. They know their cars on average get 25 miles per gallon. They want to know what they would expect to see in a sample of 100 cars. Now, the 100 cars doesn't matter here because if on average cars get 25 miles per gallon, well, then if you take a sample, what would you expect to see? So once again, listen to the question. It sounds redundant. We know our cars get 25 miles per gallon. If I took a sample, in my sample, I'd expect to see cars get 25 miles per gallon. One more time. We know our cars get 25 miles per gallon. If I were to take a sample mean, I would expect it to be 25 miles per gallon. Then down here we have what is the variation. What do you notice happens to the variation as n gets larger? As n gets larger, the variation will do what? And so we know the original standard deviation. Here's the original standard deviation. It'll get smaller. And that's the curve getting tighter. So I think it was Kyle or someone asked, what is the central limit theorem? The central limit theorem allows us to use the normal model for data. And it also shows that as our sample size goes up, the distribution will become more normal and tighter. It's one of the key components of being able to use the normal model for data. And it has two things that are central to it, that the data will become more normal and tighter as the sample size increases. Nothing happens to the mean, though. The mean, I mean, it's good to know that. The mean is the mean is the mean. It stays the mean. But the standard deviation gets smaller, and the distribution becomes more normal. And why do we want it to become normal? Because then we can use the normal methods on it. So you could have a distribution that is very, very skewed, but the distribution could become normal as you increase the sample sizes. So the key numbers to know right here, so there's a distribution that is skewed, and it becomes more and more normal and tighter as you increase the sample size. So eventually it becomes normal enough. Now the key numbers to know are 25 and 100. How did Brian describe? Yeah, we'll do some more, Jack. You got it. How did Brian describe the distribution of cars that Ford makes? Brian said the cars were what? Brian said those cars are very what? The cars were very what? They were very skewed. So a lot of people are very confused on this third condition, and I want to make sure you understand. So can anyone tell me, is the third condition met here? Do we have a large enough sample size? Brian said it's very skewed. Is his sample size of 100 large enough? So look at what it says. It says 100 may be required for very skewed populations. But wait a minute, what's my sample size? I said my sample size is this. So the condition is met. So the real quick cliff notes on this are the following. Here's the cliff notes on the third condition. This is big. A lot of people ask me about this third condition. They're like, what's the third condition? What's nearly normal mean? What's large enough? This condition is either called, it goes by two names. We're going to call it large enough n, and it'll also be part of the nearly normal. Nearly normal is a bigger version of it. We'll talk about that maybe by the end of today, I think. But I allow these to be used interchangeably. I don't care which one you call it, as long as you give the right understanding of it. I'll do this way. I got to do a slow run first here, Camden, and then we might do some speed runs. I don't want to go too quick through this, because you'll see this will make, I hope this makes sense. And then call for a speed run if you want, because I'll do it, Camden, you bet. So what we have here is the third condition for all quantitative data, and I will accept either name for it. You might see either name, because now it's more multiple choice more than you writing it, but I can explain the differences, and I will when we start talking about normal, nearly normal. So large enough n. I just want you to think about what you're saying with large enough n. N needs to be what enough? Just tell me in the chat. Tell me. Large enough n means that the n, the sample size, and I guess we should maybe do lowercase if we want, the n, the sample size, large enough. What do you mean by, when does it need to be large enough? What's going on right here? Well, the more skewed it is, the more skewed the distribution is, 20 points, everyone giving answers right here. The more skewed it is, the larger n needs to be. So let's say Brian tells you the parent population is normal. If it's normal, the rule is 1. Did everyone hear that? I'm gonna ask a question later on. If you remember this, you'll get it right. If the parent population, the original data, like this would be like Ford knows that its cars have a normal distribution. The cars they have, the original cars they have are normal. They take samples of one car. Well, then that follows the normal anyways, because the original data was normal. So we could use normal methods. But now we go skewed. And the magical number is 25. That is how large the sample needs to be for the distribution of the sample mean to be normal. Let me repeat that. 25 is how large our sample needs to be from this for the distribution of the sample mean to be normal. Because we're not saying that the parent population becomes normal. I can't draw a good... Sure, that's good enough. We're not saying that the parent population becomes normal. It's this distribution of the sample mean. Just to show, because this is a tough concept. This is the parent population I'm drawing. This is the distribution of the sample mean. Do you see it in here? This is like the average of these 25 dots. There'd be more black dots down here. The average of these black dots, if you did this as a repeated process, would make a distribution that is normal. So you see here's a skewed parent population. Like this is, Ford knows that its cars have a right skew to them. Just a right skew. They take a sample of 25 and want to understand the mean for the sample of 25. So it sounds weird, but this is the mean for the distribution of sample means. It doesn't say sample means there, but it should. This is the mean. This is the mean of this distribution, which is a distribution of 25 observations. It's the mean for the distribution of the sample means you get. Does that make more sense right there, Neelan? This down here, this mean is the mean for the distribution of sample means that were obtained. You can see each sample mean being obtained, and we keep doing this process repeatedly, and here is one of those means down here. And then we can get another one, and if we did this repeatedly, we would get a distribution that would have a mean for the distribution of sample means and a standard deviation for the distribution of sample means. It's no longer the original cars. It's what we would see. What's so magical? It's central limit theorem. And 25 isn't great. Neil, great question. 100 points. 25 really isn't a magic number. It's just a good. And what do we mean by skewed? We could really go into some statistical theory on this. Like this right here, central limit theorem, just to show you. Why not? Let's hear it. Really good questions. I love these. We're going to the site where everyone goes to learn. You know where we're going. You know where we're going. Wikipedia, the central limit theorem. I could probably learn a good bit on it, but they go through here. They show the proofs for it, and they show the distributions becoming more normal, and they go through all the mathematics, the matrix algebra on it, and go through, like, that might be the proof right here, is it? Multidimensional central limit theorem. So there's high dimension central limit theorem. But this is, you know, the whole, if we go to proof, they should have the proof on the screen, do they not? Like, it should be on here on this article somewhere. This led to the first proof. Yeah, so people have shown this via proofs of the central limit theorem. Yeah, it's big mass. It's people have shown it, and now look at this. They might, and there's issues with the central limit theorem sometimes, but it's so cool. And then they're showing right here, as the sample size increases, they're probably showing the normality. Yeah, here they're showing, here you have a uniform distribution, and the uniform distribution actually becomes normal a lot quicker. So they're showing like a uniform distribution becoming more normal, but they go through and really cool article and everything on it. It's using a lot of proofs. Yeah, it's a very big, and we call it a theorem. I think maybe a lot of people know this, but the theorem is a mathematical proof. I like that right there, Neeland. So don't worry, that went a little more in depth on it, but I want you guys to always have that kind of little peek into the higher level on it. It's big mass. It's very important. And that's stats contribution to the math world. That's us. Or we're taking that. That's the stats people's thing. No divide, but so the other magical number you need to know is very skewed. Now, this is the stat to one version of learning it, is that if it's very skewed, the sample size would need to be what? And this kind of goes back. This goes back to what we call the condition. That's 100 points right there. So what is the condition called? The large enough sample size, the large enough n. So the more what it is, the what or n needs to be. The more what it is, the what or n needs to be. The whole idea of it being larger is based on how skewed it is. We'll say it on the test question. Don't worry, in Kyle with like higher order stuff, this can get complicated in like high level statistics. But usually, here's what I would do. Let's say Brian's doing some stats, and Brian sees this right here. Brian, for some reason, is only taking a sample size of 2. But this is the way I have data on my parent population. I know it looks like this, which means we've been collecting data at the Ford factory on the mile per gallons of our cars. We've looked at the historic data. We see what it looks like. We know, do you see I'm telling you this is mu? I know that the distribution is normal with a mean of 16 miles per gallon. We're looking at some sort of our trucks with a standard deviation of 5. So you know what I could do to you? I could do right here? I could tell you the mean for the bottom distribution. The mean is going to be what? If I were to take 2 cars and average them together, I would see on average this for a sample of 2 cars. What would be the mean of the bottom distribution? The mean for the bottom distribution would be what? I'll show you the formula as we're talking about right here. The mean for the bottom distribution is the one I've highlighted right here. I know the original distribution has 16 as its mean. The mean for the bottom distribution will be what? It'll also be 16. Who can figure out, for 200 points, Hannah, 200 points, you're the only person who answered, so boom. Who can figure out the standard deviation for the bottom distribution? Who can figure out the standard deviation? So I'm going to show you the formula so you can figure it out. Remember, it was 5, I think, originally. Who can figure out the standard deviation for the bottom distribution? Who knows it? I think it's 3 something. I'm trying to figure out in my head, which is not a 3.5 or something. No, 3.6. Is it 3.1? I'll have to double check my work. I'm doing it in my head. Is it? Okay, let me check. 2 square root 5 divided by that. No! Duh. Sorry, I took a wrong guess first. You guys might be behind in the video. What did Brian do? What did Brian do to figure out the new standard deviation? Nice job right there. So, yep. That's what we have right there. And then it's 4-1 technically. I think you just reversed a number on there. That's it right there. Kind of repeats. It's like 1.414. It's almost 1 again. Where are we getting these numbers from? This right here is the square root of 2. Does that make sense? Is it making sense? Because look at the formula. The formula states we take the original standard deviation of 5. I can't change that? Why are you letting me highlight if I can't change it? We take the original standard deviation of 5, and we divide that by square root of 2. So that is equal to 3.5 or so. It's very close to 3.5. Does that make sense right there? That we take the original standard deviation and divide it by the square root of the sample size. And this is what people often, 2 comes from, I'm taking 2 cars and averaging them together. I'm going to take 2 cars and average, wow, they were both the same. So they'd average to this. I take 2 cars and there's the average. So I'm taking the mean of 2 cars. Does that make sense right there, Jack? 100 points, Jack. Thanks for keep asking. I like all the questions. We take 2 cars and we average them together. And we just figured out what the mean and the standard deviation would be. Does everyone see? We already figured out. I'll simulate more so the mean becomes it. We knew that the mean would be this and the standard deviation would be this. And I think it might round up. Let's look what it rounded to. We divide 5 by this, and it rounds up to 3.54. And look, this number right here, let's highlight it. We were able to figure out mathematically via just the mathematics of the central limit theorem. That rounds to 3.54. And there it is right there. We figured that out. Yes, this is a tough thing. That's why we're doing it slowly. That's why I didn't want to do a speed run on this right now, because it's a tough concept. And so with this right here, how did I know? Be careful. This is where I usually trick people. And I didn't want to give away the answer yet, but I want to show it. How did I know the distribution would be normal? The distribution was normal if you saw it, but I told you the parent population. Do you see here it says parent population? The parent population right here is this, and it was normal. Oh, you can do a custom. Let me do custom. The parent population, this is not on the exam today, not on the exam. The parent population was normal, so the distribution down below is normal because there's no sample size requirement. If the original distribution is normal, then the distribution of the sample mean will be normal because everything I've been talking about right here is the central limit theorem. Did you find that from the getting the normal standard deviation squared? Yep. You got it, Hannah. Yep. Because the square root of 1 is to 1, which means yeah, and that's the thing. If we could do 1 right here, you would just so Zulon's right. Zulon, 100 points. Zulon, you're at 250. That's an amazing comment. It's a weird kind of theoretical example that if you did a sample of 1, which this applet won't let us do, you would just make this distribution right here, and you'd get 5 over square root of 1, and a sample of 1 would reproduce the parent population. Zulon, do you understand that, and other people? That if you were to do a sample size of 1 and average it, it would just turn out to be the parent population, and it would still look normal, which confirms for us the parent population is normal. This distribution down here would be normal. It would have the same mean and the same standard deviation because it would be 5 over square root of 1. So 5 over square root of 1 is 5. So it wouldn't change it because it's just single observations. And we would just create the parent population again, which is single observations. I think what gets people is that this is confusing because this is the distribution of 2 values averaged together. Just so you can see, every blue dot down here is 2 averaged together. But if I increase this to 25, the distribution will be much, much wider. I'm doing it. 500-point question. First person to tell me the new standard deviation. 500-point question. First person to tell me the new standard deviation of the bottom graphic. Thomas, I'm throwing you. You're at 200, Thomas, but you got to tell me the new standard deviation. New standard deviation of the bottom graphic is what? Who's got it? You got to tell me. Well, you got to tell me what it is. You got to give me the numeric value. This would be an amazing test question. Zulon, you got it. It's 1. Right there. I'm throwing Josh, Devin, and Elizabeth, and Neil in 200 points right there. 200 is kind of the max unless I break the rules. But you are right. How did we know that? How did we know it like this? Because guess what the square root of 25 is? Square root of 25 is 5. And 5 divided by 5, which is the original standard deviation, is 1. And look at how much tighter this is. It's also normal and tighter. It was normal to begin with, but it became a lot tighter. So, amazing job right there. Sorry, I throw some crazy points out because it's like you should really know that. And when you see it, you're like, oh, we're just taking the original standard deviation right here and dividing it by the square root of the sample size to get the new standard deviation for the distribution of the sample mean. Don't worry, so many people are on track with points. I know I went a little crazy with the points. I like going crazy with points every once in a while. And it shows you're really on track. And those are tough questions. Okay. So, everything we just covered right here, there's examples. Let's do the speed run of the Brady problem. You ready? We're going to do speed run of the Brady problem. It gives the answers later here. So we're going to speed run the Brady problem. We're going to do... Okay, let's do this, though. After the speed run, don't leave. I'm going to do one more chapter today, which we've kind of already done. Not chapter, but the remainder of this, which I've already covered it, actually. But we're going to go through the notes on it. If you were here for the start, which you should be, you've already seen it. So let's do a speed run. Let's get speed run timer up. After speed run, we'll have a 5-minute break, but don't leave because we are covering a little bit more new material. Probably the last 15 minutes of class, we'll start getting into doing assignments. We did do all the work yesterday. I think we did a lot of the conference roll stuff in yesterday's video. So if you're waiting for the video to post or the timestamps, I did add the timestamps to yesterday's videos. Don't leave. There is new material still left after this speed run right here. Let's hop into the speed run screen. There's our commands. Look at that. I'm already fixing the timer. I don't got the screen up for the thing, though. Okay. So, let me think. What is the numbers? I just need to know the numbers for the Brady problem. Is it 176? Well, then, guess what the answers. Okay. So, the Brady problem says, here we go. Let me copy all this. Boop. Let's go here. Let's drop it into here. Okay. Here's a speed run of the Brady problem. We're going to do, what time are we going for? I'm going to go for sub 5 is perfect. You ready? Sub 5. Let's go speed run. We got this. Okay. When we are talking about the sampling distribution of the sample mean, there's 2 equations we should know. The 2 equations we should know off the top of our head, but will be given to us on our formula sheet, are that the mean for the distribution of the sample mean is equal to the mean. And this is one of those obvious things, like when we say, if we know from adults, this is apparently giving us, we know from adults that the mean of adults' weight is 176. Well, that 176 right here is given to us, and we're saying we know this is true. So now we've answered this question right here, that the average weight of adults is 176. So guess what? If we took a sample of adults, we would expect to see 176, and that's what this says. I would expect to see in a sample 176. Now we see that the standard deviation for the distribution of the sample mean, which is the 2 things we need, the standard deviation for the distribution of the sample mean is equal to the original standard deviation over the square root of the sample size. This is 2 parts of the central limit theorem right here, or one of the 2 parts, because as n gets larger, this will get smaller. The standard deviation will get smaller, i.e. tighter, as we increase the sample size. So let's go ahead and plug in our numbers. Always know your notation. We have here that we have a standard deviation of 61, and we are taking a sample of 100 people. So I've marked my notation. Right here's my 100 people, and there's my original standard deviation. Now this problem's amazing because square root of 100 is going to be a very nice number. Square root of 100 is going to turn out to 10, which means we know that our new standard deviation for the distribution of the sample mean is equal to 6.1. Now, once you have this, we need to check one last thing here. The last thing we need to check is to see if this is going to be normally distributed. Now, it does say, and this is condition number 3, that we need to know the distribution shape of it, but here's the numbers for the rules. I'm going to pop up the other screen here because we've already got some shorthand for it. Here's our numbers. We have that if the distribution is normal, that we need at least a sample size of 1. If it is skewed, we need a sample size of at least 25 for this distribution here to be normal. If it is very skewed, we need a sample size of at least 100. So in this class especially, there we go, it should just be overlapping. In this class especially, 100 is pretty much good for anything. I say pretty much, we're not going to try to trick you, but 100 is kind of like 100 works for everything in this class. There's a lot more to the central limit theorem that we have not told you yet, but you won't be tested on this class. So 100 pretty much works for anything. Not the F distribution. Okay, 100 pretty much works for everything. Okay, I'm going to stop talking outside this class. So we have a sample size of 100 here. With the sample size of 100, we pass the 3rd condition. It'll be normal enough. Condition 1, randomly selected people. Condition 2, these people are less than 10% of all people. Condition 3, the distribution will be normal due to the large enough n. Passing all 3 conditions tells us that we can use these normal methods. So guess what we're going to do? We're going to draw out this distribution now. Let's draw out the distribution. We're going to go right here. We're going to draw it in black right here. We thought we had the black pen selected. Now we do. Here's our distribution of weights. That is the worst normal I've ever drawn. That's a decent normal. We can take that one. Here's the mean of it. There's the mean of the distribution. And now we scroll down just a little bit. And we put here 176 because that's the mean. We go up 1, 2, 3. We go down 1, 2, 3. And then we go up 6.1, which is 182.1, 188.2, and 194. My nines look horrible. 194.3. So I'm just going up and down those standard deviations. Now it says he wonders if his balcony is designed to support 1,900 pounds. So 1,900 pounds is going to be over 100 people, an average person weighing 190. So you can see where 190 is at. 190 is going to be right about here. Now I want you to think for a moment, what is the z-score of 190? And you should have a decent guess. Now the z-score, which is the last formula we need to know for this, is simply what we observed in our sample minus what we would have expected over the standard deviation divided by square root of n, which we've already found all of these numbers. Plugging in the numbers, we take that we observe a mean of 190, we expect a standard deviation of 176, and we divide that by 6.1, and we do get a number very close to where we put our line. Nice job if you're following along, you got that z-score. We've kind of solved it. I'm not going to go sub 5 here. We're kind of in the bonus right now, but we've found the z-score, and this seems kind of unusual. Now, what we need to do is we need to go to the David M. Lane applet and put this in here to find the probability, because he wants to know what percent of the time would people be over this. We have the z-score, and let's show this two separate ways right here. We're going to hop over to here. Let's go to David M. Lane. I'm going to have to break the speedrun screen. So we've got David M. Lane up. We're going to have to hop out of the speedrun screen for a half a second. On the David M. Lane applet, we're going to put into here the mean and standard deviation and z-score. There's the answer to our problem. We have now solved the problem and found a probability of about 1%. We could also put in the mean of 176 and the standard deviation of 6.1 and then go above 190, and it's on the same spot on the curve. If you were to go between the answers, here's with the numbers on the curve, and here's with the z-scores. Same answers. 190 is, just to repeat, good question right there. 190 was found. Go back to speedrun screen. Oops, wrong screen. Never done that before. 190 was because we have a sample of 100 people, and he wants to know if it can support 19,000 pounds. And so to find 190, I found he has 19,000 limit for 100 people. The average person can weigh up to 190. Does that make sense? Because this is, if the balcony has a limit of 19,000 pounds and we're going to put 100 people on it. And so this means, what this question means, and just think about this scary nature of it. If you were to say, and this is, we'll be done to 1 minute here, then we're going to take a 5-minute break, and then we are doing more lecture when we return. Don't leave. Make sure to stay. If you were to take samples of 100 people on a balcony, the balcony, if it breaks at 19,000 pounds, 1% of the time, it would break. And that's kind of scary, because think about this. This means like 1% of parties where people weigh 100 pounds. And this isn't saying like maybe if the NFL throws a party, well, then it's definitely going to break because they weigh more than that. Sorry, NFL players, you do. But just due to random variation in the data, 1% of the time, a party of 100 people would break the balcony. And that's kind of scary. Just think if this is a balcony like you rent out like every weekend for like 10 years. Well, it's probably going to break. We could do the math on that. Yeah, I was spitting fire at those NFL players. But so it's unlikely, but over repeated trials, yeah, it's kind of scary. And I would say, even though it's only 1% in the business context, it's like, you need to up that. Imagine now he reinforces his balcony. So now he reinforces it to where it has a limit of 20,000. And it is with just random people. If it has a limit of 20,000, then we would change this right here. We could go back over here, and we put in our mean of 176, our standard deviation of 6.1, and then we go to here and put in 200, and now the probability is basically 0. And I would use something to calculate this more finely, but it's off the chart. You can see it's at a z-score of about 4. You could figure out the z-score with, and I agree. Zulon, great advice right there. We want to be further out. And usually people do things within what we say, and I think Isaac and I were talking about this a while ago, 6 sigma specifications. So usually you try to do 6 sigma. So in truth, if we're doing this like the pure statistical way, you would go 6 standard deviations above it. So we'd times this by 6, and then we would add this to this, and then we would times that by 100 people, and that's the limit he should try to get. So if I was talking to him as like someone who does statistics, I would say you should probably get a specification at least above 21,000 pounds. So 6 standard, and that's a really safe metric, because then it's like 1 in like 4 million random parties would break it. It's like, and at that point, you'd probably notice like, hey, everyone at our parties, a lot bigger than the average American. Maybe the 100-person limit, maybe it says 100 people, but it probably doesn't expect us all to be 250, 300, 400 pounds. But this is the average once again, because if it's like, yeah. And yeah, I mean, I know I'm talking about weight and stuff like that, but if something says 100-person limit, they don't mean 100 babies, and they don't mean 100 people who weigh 500 pounds. Those specifications are given for like average American, based on the data. And then you say, well, that changes over time. It does. That's why data is hard to deal with. Data is fun. Data is crazy. So, yeah, that's got it. Take the break. Let's hop back to the speedrun screen. Speedrun. Pretty fun problem right there. Decently tough chapter. We'll start doing some of the work for this. We'll definitely do a lot of work during office hours. You guys know we go a while during office hours and stuff. Take a break. Set timer for 5 minutes.
Okay, 5 minutes and counting.
When we return, the chapter we're doing is just over confidence intervals. You'll be like, we already did this today. You already told us about it. 5-minute nap ready to go. I'll take a nap too. People just tune in the stream. YouTube will cut me off. They'll tune into the stream here. Yep, chapter 14 still due tonight. There's still wait, isn't it? Confidence rolls are due tonight, right? There's only one thing due tonight, right? Let me double check. There's one quiz due tonight, right? Isn't it confidence rolls? Let me look at the due dates. Unless I've made a mistake. Let me check this during break right here. I think I've made one thing due on each night for the remainder of the semester, like one quiz. My hair is so long now. I've changed around due dates a few times. Quizzes and tests. Okay. Today is the 21st. There's only one thing due tonight, and it's chapter 13, right? Unless I've made an error on the homework, that might be where the error is. Because multiple people have said this now, and that's when I start to look. Oh, yeah, the homework says it's due. Let's change that. That's why people are saying it. 100 points, whoever was telling me that. Why not? You're at 200. I really appreciate that. This should be due on the Wednesday. Okay, that's why people were saying, but this is due. All right, fixed. And all those are fixed. I think everything's right now. Okay. I think everything is correct. Let's go back. Back. Yep. Sorry about that. No, that's where the confusion was. So now it should just say 13 quiz. Sorry about that. No, and I appreciate that. The quizzes. So this is what we covered right now is test 3 material. And so it's not due until the homeworks are not due until the tests are happening. Thank you guys for pointing that out. I appreciate it. I don't want to put too many things due on a date. I know we have a lot of work in this class, and you guys have been doing great. It's mini term. Mini term is an everyday thing. Woohoo! Hop back over here to lecture. Mini term is tough, but we are doing it. We are wrecking mini term. We got this. Mini term. What assignments are we doing after class? We can do whatever you guys want. If you stay, you get to pick. So, Devin, hang out, chill, and be like, hey, Brian, do this question. Just put the question in the chat right away, and I'll do it. There's a question like a philanthropic organization is using ballots to mail out. I'm having a hard time with that one. Yeah, Christina, that's the one we did from yesterday, right? For that one, Christina, identify, I think it gives you X and it gives you N. And from X and N, we can get P hat. And so we have X, we have N, we get P hat. Does that make sense, Christina, right there? And then from that, you will figure out P hat plus or minus Z, P hat times Q hat over N square root. What part of that are you stuck on right there? I have it all set up right, but my answers are wrong every time. Do you have the right Z-score? Tell me what your Z-score is and tell me what your percent confidence is. I'll make sure your Z-score is correct. So what Z-score are you using? What is your Z-score and what's your percent confidence? 2020 is a crazy year. So yeah, what Z-score do you have and what percent confidence are you using? Because that's a lot of times where the error is, I think. A lot of times people have the wrong Z-score. And I have done a lot of Z-scores. Unless I give you something weird like 92%, then I'll have to look that one up. Because no one does a 92% confidence roll. It's only done to test students to see if you know how to find it. I mean, it's a good way to be like, do you know how to find a 92% confidence roll? And like, we just don't. It's not something I memorize. 92% would be between 1.96 and 2.3263, but it might not be. Yeah, it's like, you can use the Z-score table if you want. Yep, that's correct, Christina. That is the right Z-score. 1.645 is for a 90%. That is correct. Yep. I think it's 1.6449. I can double check. I like doing this. I like, you guys know me. We'll be. You might have to send it to me, Christina. I'll take a look. The Z-score, so I need to go here to P-norm. No, Q-norm. It is, yeah, 1.6449. And so this right here, see, watch this. This is why power of coding real quick. Oh, scaring my phone there. Okay. So I can write a function right here if I don't know how to use this. And we need to put in, someone wants to put in like a 90% confidence interval. So this needs to be, so wait, this will be X. They'll put in X. If they put in 90%, 90% would be 1 minus X, and then we divide that by 2. So, and then we need to take, and then we need to go absolute value of it. So this should do it. Absolute value right there. Okay. So find Z. So this function right here should find the Z-score. So now my function that I've written, if someone enters in like this right here, like 90%, there's the Z-score for a 90% confidence roll. If someone enters in like 92, it'll do this. If you enter in 95, it'll do this. And so this function I've written right here, this function will find for me the Z-score no matter what I enter in. So if someone's like, what's the 98%? What's the 99%? It can do this right here. And I could enter in other arguments, just seeing real briefly, then we'll finish up lecture today. I could enter another argument like here called rounding, or like I could call it R for rounding. And I would go right here and go round. And we would put in another argument. We'd put the R here for the round value. And so now it has another thing. We'll put this by default to 3 decimals. A lot of people like 3 decimals. And so now we run this. And oh, what's going on? R equals, it's not an equal, right? Yeah, that's not right. What did I break? 2 seconds. Okay, that worked. Multiple arguments returns are not, oh, wait. Round this. Oh, that's why. 2 seconds. Parentheses error. That's the thing with code. One error in your code breaks. So now someone can specify how many decimals they want this returned to. So you can specify the amount of decimals. This is why I love the power coding. My N was 100,000. My X was this. My P hat is this. My Q hat is this. So let's take your numbers, Christina, right here. Let's do this real quick for Christina. We're going to confirm Christina's answers. She's got her X and she's got her N. So we've got her P hat right here. So we're going to take Christina's P hat right here. And there's her P hat. There's her Q hat. And your, what percent confidence was 90%? And so your interval should be this right here, Christina. So your interval should be 0.0477 to 0.0500. Does this look correct? Are you getting something close to this, Christina? There's your interval right there. And so I was working this one yesterday, and we're going to hop back to lecture here in 2 seconds. But I always like showing off what coding can do because, you know, I just find it fascinating. I'm going to stop. What'd I do? Oh, do I not have a nice... There. That's where the error is. Paste. So now it even tells the user, and you could put this online. Like I could literally, I should do these things. I could literally put this online as an applet right now, and you could just put in the % confidence you want, and then it would return to you this sentence. It would say the z-score to use is this, and I can put it to 3 decimals right here, and it'll do that 1.645. So so I did I write it wrong right here? Should be 49, technically. Yep, because there it is right there. So this is what I like about code, obviously. It's just like, well, you can make it a sentence, all that good stuff. So let's hop back and finish off the lecture. Woo! Coding, I don't know. It's just fun. See, I can't do it or I'll get too wrapped up in the code. It's difficult. There's a learning curve. It's like playing an instrument. It's just like the more you practice, the better you get. You just got to practice, and that's the hardest thing. Yep. Great job, Christina. Glad to help you out. I know you've been working hard. We were emailing yesterday. Great work. Keep it up. Keep up the hard work. So that was your ask during the break. You got it during the break. Here is the last topic for the day, and we should be done with like 15 minutes because we don't have much to talk about in this. We've talked about a confidence interval for the mean. To make a confidence interval for the mean, what are we talking about before this? Wait, gotta put the check mark. To make a confidence interval for the mean, we're making a confidence interval for the what mean. To make a confidence interval for the mean, we're making a confidence interval for the what mean. Like, what confidence interval are we making for the what mean? For the 200 points, who knows? For the what mean? Which mean are we making a confidence interval for? We're making a confidence interval from the sample mean for the true mean of the population. So we're making a confidence interval from the sample mean for the true mean. Because remember, the confidence interval is going to be made from the sample because the sample will be used to estimate the truth. Big key things to understand about this. That every time we make a confidence interval, it's made from a sample. The sample is your estimate to figure out the truth, to estimate the truth. So, wait a minute. This is kind of obvious. Just 1.96 for a 95% confidence interval. We've been doing that. And then wait a minute. We've already seen sigma over square root of n. Wasn't that what we were doing literally just a moment ago? We were literally just doing sigma over square root of n, because as the sample size gets larger, the standard deviation will get smaller. That's so easy. But wait a minute. We don't know what sigma is anymore. So, well, let's just change sigma to s. I mean, if we don't know what sigma is, let's just change the sigma right here to an s. Let's just do that. We don't know what sigma is, so let's just change that. But now there's a problem. This is not accurate anymore. So now the z is not working. Well, we need to call someone. We need to call someone to help us out. Who knows in the chat who we're going to call to help us out? We're picking this picture of him today. Who knows in the chat who we're going to help out? Who's going to call us to help out? Between two pictures. I like this one. I like the other one. Just chat no who we're calling to help out. Close. I could start using that, but no. We're not calling Ice-T. We're calling Mr. T. Mr. T has been called to help out. I like that picture. You got some classic pictures in here. We got like classic Mr. T right here. Here's your goes classic Mr. T. Where's another Mr. T? We got like Mr. T. You need to like get your life together, Mr. T. Not him. He's got his life together. But this is Mr. T like, you need to get your life together. Like, oh, this is 80s Mr. T. Oh, we got to end off with 80s Mr. T. There's so many Mr. T's and they're all awesome. Oh my God. This might be my favorite Mr. T. It's so classic. Oh man. Mr. T, and he's like 70 now, and he's still strong as ever, Mr. T. Well, Mr. T is so awesome. I know. I want to do a video with Mr. T about the T distribution because Mr. T is the reason we have the T distribution. I want to explain to you what goes on right here. I'm going to do my horrible Mr. T impression in just a second. But here we go to the main screen, talk about Mr. T. Oh, we're already on it? I guess we are. So, here is the T distribution. It looks kind of normal. This distribution right here is the Mr. T distribution, though. And every Mr. T distribution has with it what? Every T distribution has with it what? You need to know this. Every T distribution has with it what? You tell me. Who knows? It's that thing I'm highlighting. You can say the abbreviation. You need to know this. Every T distribution has with it these. Anyone know? No one knows. Degrees of freedom. DF. Those stand for degrees of freedom. Because Mr. T is the reason this is normal. He comes over here and he says, he goes, gotta go over here to this. He goes, I'll pay the fool. And he smashes it down. So Mr. T goes in, smashes it down. So Mr. T just smashes down that normal. But guess what? Mr. T's a nice guy. He will give it degrees of freedom to be more normal. And wait a minute. Didn't we just talk about 1.96? We said that the value for a 95% confidence interval, which this is because it's got 5% on the outside, if you don't believe me. Well, there's 95% on the inside. That's a 95% confidence interval. And the T-score is 1.96. Because now, this is basically normal. But what if Mr. T doesn't give it the freedom to be normal? Well, now, all of a sudden, the T-score is very different. The T-score with 1 degree of freedom to be normal is 12.71. But as it gets more degrees of freedom, it goes towards 1.96. Now, it truthfully never is 1.96. There'd be decimal places beyond this that we can't see. It just approaches. You can see it basically, look as it gets closer with more degrees of freedom. It's getting really close. And now the decimals are so far back that we don't really see them. It's just basically 1.96. And for all intents and purposes, it's 1.96. So the degrees of freedom, unless they're infinite, then it would be normal. So only when there's infinite degrees of freedom. But usually most statisticians only care about calculating after 60. And I really like 60 because at this point, the correct T-score with 60 degrees of freedom is what? For a 95% confidence interval with 60 degrees of freedom, the correct T-score is what? It's on the screen. And this kind of goes to your 68, 95. The correct T-score with 60 degrees of freedom is actually this. That's the right number. No longer is it this number. The correct number is this. It's 2, which follows our 68, 95, 99.7. I bet you if we go to a T of 3, what do you think? Who can guess what percent of data on a T curve with 60 degrees of freedom, what percent of the data will be contained within plus or minus T scores of -3, +3? Probably going to be close to 99.7. Now, it's not exactly 99.7 because it's the T curve. If I were to add in more degrees of freedom, now it's 99.7, but it was very, very close to. But what if I delete the degrees of freedom? Now it's nowhere close to it. Now the numbers are very different. Now, with 3 standard errors on this curve, only 79.5%. So what must you know for every T curve? Every T curve, you must know this. You must know this. This is the biggest note you could ever take on this. You must know this for every T curve. You have to know this. You have to know the degrees of freedom. The more degrees of freedom, the more normal it is. Yep. As there's more degrees of freedom, the curve becomes more normal. And so there's a lot more to the theory of it, of course, but understanding that degrees of freedom draw the curve for you, and the more degrees of freedom it is, the more normal it is. Do you guys want to know the really super complicated formula? I'm probably going to need maybe around 3 sheets of paper. Oh, you know what? I'm going to try to speed run writing this with just 1 sheet of paper. Okay, so I got 1 sheet of paper to write the formula for the degrees of freedom. You ready? You guys, I want you to memorize this. Here's the formula for the degrees of freedom for the 1 sample T. Yeah. That's it. That's it. Remember, one sample t, n minus 1. One sample t, n minus 1. So if I'm doing a one sample t, it's n minus 1. Thank you. It's just n minus 1. Don't worry. Don't worry. So if you look at some of our later problems for this, I'll tell you the actual story in a second. The actual story is fun too. Can anyone tell me? We can already start doing some of the problems if we wanted. The sample size here is 23 cars. Can anyone tell me the degrees of freedom? Nice notes in the chat, 20 points. Can anyone tell me the degrees of freedom for this? Can anyone tell me the degrees of freedom for this? There's 23 cars. 22. Boom. You got it. The degrees of freedom are 22. Yep. Now what you have to do is when you know the degrees of freedom, you have to go to the t-applet. This is where people get stuck. This, what I'm telling you right now, is the biggest thing people get stuck on. You have to take the degrees of freedom, immediately put them into the t-applet, then put in your confidence level, and there's the t-score for a 90% confidence roll with 22 degrees of freedom. This is where people get stuck on the quizzes. They say, how do I get the t-score? Every time you try to get a t-score, you must know the degrees of freedom. Well, the degrees of freedom are n minus 1, so it's 22, and I want a 90% confidence interval, so the answer to it is 1.717. And that's exactly what we found right here. Look how I input the degrees of freedom in, and I input the percent confidence, because it's a middle shading. We shade the middle of it, just so you can see that visually again. We shade the middle for the percent confidence in the middle, and then it tells us the p-value, and it's like the t-score. The t-score right here is 1.717. Does anyone think, I'm throwing 500 points in the chat, crazy points, and if you can do this, you'll be able to do a lot of the assignments. Can anyone tell me the t-score for a, when you have a sample size of 101 and you want to build a 95% confidence roll? You have a sample size of 101, you want to build a 95% confidence roll. 90, so the t-score though. You guys are close. You get 500 points. I'll say the name who gets it. You go to the applet. Let me drop the applet in the chat. Input what I sent into the applet. We have a sample size of 101, and we want a 95% confidence roll. Sample size of 101, we want a 95% confidence roll. Should have chose a smaller number because I won't be able to tell the difference. Close. Neelan might be right. I'm getting a different number in my head. I'm going to take one more answer before I say it's right, but Neelan might be right. Is it that? Go to the applet, try putting it in. You ready? Since I told you the sample size, what are the degrees of freedom? 2 people have confirmed. I said 95, right? That would change what the answer is if I said 90. I said 95. 100. And then right here, we put in 95. There it is. There's the t-score. Just depending if you were to do a 90%, that would be the t-score. Does everyone see how this works? Does that make sense? So it was Neeland, amazing work. Neeland, you can throw some of your points if you want. You might get a ton of people saying me in the chat. I know you did that yesterday. You can do it if you want. And so understanding how these t-scores are found, and the t-score is basically like the what? The t-score is just the same as the what, basically. The t-score is just like the what score. The t-score is just like the what. It's just like this. It's just like the z. It's not the z. It's very similar to the z. The t-score is going to tell us our percent confidence. And if you look at this equation right here, I prefer to look at it this way. This is the standard error of y bar. Does this equation look that complicated? It's the equation we did at the very, very start of class. I wrote it down here at the start of class. So we've already covered it. Like I was saying, we've done this. All we need to know is the sample mean. Then we find the t based on the degrees of freedom, which this is the degrees of freedom right here. This will give us the percent confidence. We know the standard deviation for our sample, and we know the sample size. This is all it is. This is this whole last part of the chapter. It's much simpler than what we did to start. So if you're here listening and understanding and following along. You know what's crazy, though? Here's the thing. Hop back to lecture stream. The actual story of what happened is about just as crazy as Mr. T time traveling and smashing down the normal curve. This dude, look at this dude right here, William Gossett. William Gossett created the T distribution. He worked at Guinness Beer, no joke. Worked at Guinness Beer. I could imagine him just drinking his beer being like, you know, our statistics are not working that well. So he went and created the T distribution. You say, well, wait a minute. Gossett. Did he call it the student T because of the T in Gossett? Maybe he did. But there was a guy, Ronald Fisher, very famous statistician, who didn't like Gossett. He's like, dude works at a brewery. What does that brewer know? So Ronald Fisher wouldn't publish Gossett's work. So Gossett made up the name Student T, submitted his work, and actually got it published under the name Student T. And just so you know, very famous story, and Guinness is very proud of this. They've got a plaque on their wall. I'll show you a picture of the plaque right here. So Gossett, there's Mr. T. I'm sorry, Mr. T, you don't get credit for this one. But chief chemist and statistician William Gossett right there. So William Stanley Gossett or something like that. William Seeley Gossett, there's his name. But he worked at Guinness, and this is within their thing. So, and they should have put a plaque to Mr. T next to it. I have been trying to get a hold of Mr. T. Probably is like, yeah, but I want to make a video with him where he time travels and we make the T distribution. So, real true story. Dude was making beer. Oh, you saw it when you went to the factory? That's so awesome, Josh. Well, now you're being like in stats class. He's the reason we have the distribution. He was sitting around making beer and being like, you know what? We can make stats better and beer better. And he did it. He made the T distribution. It's changed statistics. So, is he on Cameo? Hey, well, I want to do like a whole video with him. I'd take a cameo from him. Maybe I should look into that. He might be. So it's all about this. Please note that the T distribution is smashed down. Mr. T comes in, he says, I'll pay the fool. And he smashes down this distribution. Once again, we saw this, that the T has wider tails. So your T interval will always be wider than a Z interval. Does everyone see here? Here's the T smashed down. And you can see it visually. I'll try to put it in the background here so we can see it. Watch as Mr. T smashes it down. So here it is. He's going to smash it down. You ready? I'll pay the fool. And then he starts to let it go back up. He's giving it degrees of freedom. It's very hard to see from that angle. But that is the T getting smashed down when it doesn't have a lot of degrees of freedom. So that is the T getting smashed down right there. Mr. T, the man. So he beat Rocky. And then Rocky cheated. Rocky cheating. Ivan Drago is still the best. That's the best villain. It's like, I will break you. Rocky 4. And then Rocky... I've heard the new ones are good. I need to watch Creed. Has anyone seen Creed and Creed 2? Because that's Michael B. Jordan, right? Am I correct? Michael B. Jordan's awesome. Is he... It's not Michael B. Jordan, is it? People tell me good things about Creed. I just don't watch nearly as many movies. Is it Michael B. Jordan? Because he's... Last rant... Black Panther, Michael B. Jordan in Black Panther. Michael B. Jordan is like his villain in Black Panther, one of the top Marvel villains. I mean, I put him up there with Obadiah Stane, but like so good. He just like the way he played that character, so good. So good. Like that's like one of those scene-stealing moments. That's like Joker versus Batman, where Joker was so awesome. But I mean, Black Panther's awesome too, but Michael B. Jordan just he's the man. Okay. Yeah, I should definitely watch both Creeds. I've heard good things about the Creeds. I got burnt out on the last few Rockies. Like once Rocky 5 went and then Balboa, and I was like, ah. And then I just don't watch nearly as many movies these days. So I'll try to check out both Creeds eventually because I've heard good things. We did the Kahoot yesterday. Not officers yet, so I gotta stay a little bit more on track. Here we go. Condition 1. We got our randomness. We need to randomly select our data. Condition 1, random. Condition 2, less than 10%. Condition 3 is going to be nearly normal. I alluded to this earlier. Now, nearly normal means that the distribution should generally follow the normal. It's basically the same thing as large enough. It's basically the same thing as large enough n. I don't mind if you interchange them. Where's that large enough n condition? Here it is here. I kind of alluded to it that it's like, and I don't care if you call them interchangeably. They're basically the same thing. Nearly normal means that the distribution's shape is basically normal. It can be checked by large enough n. I always hate this slide because it changes the numbers, but you can check it via the large enough n. As in, the larger n is, the more skewed the original distribution can be. You can still use numbers of 25 and 100. I'm fine with that. The book slightly changes it, and our slides mirror the book in case anyone's following the book, so we couldn't change the slides too drastically. But still, it generally works that if you have a smaller distribution, then the sample size, if you have a more normal distribution, the sample size can be smaller, more normal, smaller. Skewed needs to be bigger. Very skewed needs to be very large. So it's kind of the same idea of large enough n. But also, we can check to see if it's normal. You'll see that in a half second here. I'll show it in a moment. I'll show it right now because we're talking about it. Tell me, does the distribution follow the QQ plot, yes or no? Does this distribution right here follow the normality on the QQ plot, yes or no? Does it follow it? Does that follow the red line, which shows us normality? I would say, does it follow the red line? Yeah, it does. Does it look unimodal and symmetric? Yeah, it does. Do we pass the goodness of fit test? Yeah, we do. Do you think this is nearly normal data? Do you think it's pretty good? It's definitely pretty good. We don't even need to use the last way of knowing. The last way of knowing is to say we took a sample size of 23 cars. So a sample of 23 cars would probably not need, it couldn't be very skewed. This has very, very little skew to it, if anything. There's one outlier. So if you were to go beyond, which is what you can do with the large enough n condition, like if this was very skewed, we'd have a problem. But we don't need a very large sample size because it's mostly normal. So since it's mostly normal, the sample size of 23 is large enough. So nearly normal. Let me explain the difference between nearly normal and large enough. Nearly normal is this right here that I have on the screen. It's looking at this and saying it follows the QQ plot, it's unimodal and symmetric, it passes the goodness of fit test because we do not reject the null. We don't say we have evidence of non-normality. When you do the large enough n, you don't have this because it's theoretical. Everything I was showing earlier is theoretical. So you're saying, okay, wait a minute. The theoretical distribution, would that be normal of sample sizes of 23? And since this is mostly unimodal symmetric with very little skew, it would pass large enough n. So large enough n is kind of a subset. I know it's confusing, but it's like an advanced way of doing it. Because let's say this was very skewed, but it was a sample size of 200. So if this looked very skewed, and if it were to fail the goodness of fit test, and it had a very strong skew to it that didn't follow it, and it's got this like long tail here now, so it's very skew, is it nearly normal? Be careful. This is where the trick comes in at the end. Would it still be nearly normal? The sample size is now 200, though. The answer is, we would say yes, it is nearly normal. Although the original data is not normal, due to the large enough sample size, which this slide is covering right here, because you see it says extremely skewed. I like to use 100 as my guideline. Don't worry, I don't get too specific on that on the test. I use 1, 25, 100. So due to the large enough n, then it would be nearly normal. But what if my sample size right here is only 20? Now it's very skewed with a sample size of 20. This is bad, this is bad, this is bad, and the sample size of 20 is not enough. It's a complicated one that people often ask me to review. Don't worry, it's pretty complicated. But this completely is garbage because we only have 20 and it's very skewed. The distribution will not be normal enough, nearly normal. But in our example on the slide here, let's go through it step by step. You ready? This is good, this is good, this is good. So since everything's good, the distribution of the sample mean would also be normal. The theoretical distribution would also be normal no matter what the sample size is, because the new distribution of the sample mean would only be more normal and tighter, and this follows the rule earlier. And so I'm trying to draw a distribution that is more normal and tighter around the same mean. So we'll do it one more time. There we go. Perfect. So the new distribution of the sample mean of sample sizes of 23 would be more normal and tighter, but since the original distribution was normal, the new distribution would also be normal. So it passes by every single way we can test it. And really, this is kind of your last step to use the theoretical approach, which is important, which is contained on this slide right here. That depending on the shape of it, the more skewed it is, the larger n needs to be, which literally harkens back to the idea of large enough n right here on this slide right here. That's why I spent so much time on large enough n. And I still use the numbers of 25 and 100. They're just good guidelines because there's no magic number. We're going to go pretty much the whole class because I'm going to cover the last few examples right here. We've talked about how to find... We just got the example. Here, let's do this. Let's do a homework question and see if we can do it. You ready? Let's hop to the homework and see if we can do a homework question. Just to show you what this chapter is like, we're going to go to a homework question and try a homework question from chapter 14, excuse me. Chapter 14 homework. Chapter 14 homework. It's only 3 questions? We can do the whole homework real quick. Why not? Let's do it. And then I think Devin and others had questions. Okay. Okay. So here's the first homework question. The first homework question says, a medical researcher measured the pulse rates of people with a 95% confidence interval. Explain what this interval means. I am blank % confident that the true blank is contained between the interval blank to blank. So we are 95% confident that the interval blank to blank contains the true mean heart rate. Does everyone see what I said? I am blank % confident that the true blank is contained between the interval blank to blank. So we just use our interpretation from earlier and make sure it kind of works with it. So that will answer this question for us if we know how to interpret an interval. So we get that one right. What is the margin of error? Okay, how can we do the margin of error? We covered this at the start of class. Can anyone tell me the mathematics to get the margin of error on this? The margin of error is blank the blank of the interval. The margin of error is blank the blank of the interval. This is chapter 14, confidence intervals for the mean. We can do any other ones after this. We'll do this one. It won't be that bad. And we'll have done the homework for this chapter, which we just covered in like 20 minutes, which we did also do at the start of class too. Half the length. Okay, let's find the length of the interval. That is so many decimals. There's the upper minus the lower. There we go. It's half the length of the interval. Yep, it has 2 parts. To 1 decimal? Really? Oh, another part to this. Does everyone see here that this is basically 72 to 76? So it's basically 74 plus or minus 2. And now, can you do part B again? Okay, yep. When you do part B, you take half the length of the interval. So you take the bigger number minus the smaller number, and that tells you how far they are apart. So I just want you to pretend for a moment that the interval goes from 72 to 76, which is basically the numbers. What is half the length of 72 to 76? What is half that length from 72 to 76? 72 to 76 has half the length of what? Like half the length of that is what? Who knows in the chat? 200 points. Hint, 200 points. What is half the length of 72 to 76? Anyone know? Tricked everyone. What is half the length? You got it right there, Devin. It's 2. So you just take it, you divide it in half. That's got it. Half the length of the interval. Boom. If the researcher had calculated 90%, so they did a 95. So okay, we gotta use our hands here. You ready? 95. Should Brian's hand goes in or out to do a 90? If I go from a 95 to a 90, should my hands go out or in? Thanks, Zulum. I got it. So should my hands go out for a 90 or in for an... I'm at 95, and I should go in for a 90. 95, 90. So the margin of error would be smaller. Just good to kind of check your mind with these things to be like, okay, 95, 90 is inward. We're going to go in. Here we go. We've got hot dogs here. Let's take and start doing our notation on these. What's up, Gossett? Thinking of lemons, trying to sneeze. Identify notation. Can't do it. Okay, can anyone identify any of the notation in this problem? We need to identify notation first for any problem we're given. That's the key to success in 201. Can we identify any of the notation? I'm going to start highlighting it while you guys tell me. There are 5-ish things to identify here. Mean, you got it. So that mean right there is from a sample. So that's a sample mean we obtained. Standard deviation, that is S. And anything else? We got N. Who here can give me one of the ones that's not written on the screen? There's one last hard one to find, and I'll find it here in a moment. I'll have to find something else. 200 points. Who knows the one I haven't written on the screen that we can find from N? So we know the sample size. What else can we figure out like that from sample size? Someone's going to say it while I'm writing it. I'm going to start writing it. Oh. Yep. Good job right there, Zulon. Yep, the degrees of freedom are 49. Now that I know my degrees of freedom, what is Brian going to find right now? What is Brian going to find that he knows his percent confidence in his degrees of freedom? Brian is going to go find the what now? Brian knows his percent confidence. Brian knows his degrees of freedom. He's going to go try to find the what using this information. He knows his percent confidence, and he knows his degrees of freedom. You got it, Hannah. Hannah, amazing work right there. 200 points, Hannah. It's like the max for today. We're going to go find that T, because I know we have 49 degrees of freedom, and we're using 90% confidence, was it? Let me double check the percent confidence. 95. I knew, it's like that didn't sound right. So now we go here and put 95, and there's the T. 2.01. Degrees of freedom are n minus 1. N minus 1. Sample size minus 1. There was 50. 50 minus 1 is 49. Drop the link again. You got it. There you go. What if you got a... Oh, you're at 200. Hannah, I'll put you at 300. You excellent work. 300, Hannah. So you're at 300. 300 for the day. Remind me. Be like, Brian, you broke the rules. 300. So we gave some people a little bit more, too. We're going crazy. Don't stop coming to class. Keep learning. Keep chatting. That's how we learn. So now we just need to write our formula. Was it 2.01? So I need to write that. T equals 2.01. Now we're going to write our formula right here of y bar plus or minus t. The star means you get to pick it. So that's what that star means. And it just means it's related to the percent confidence. Because you could have said 90, 95, any sort of thing. And so now we have right here, you guys are awesome. Like, you guys helping each other out. It makes me proud. It's like, I'm not going to cry or anything. I swear I'm not going to cry. But when I see people in the chat, like, helping each other out with answers, it really makes me proud. I need to make, like, a checklist for what you can do during class. You guys can help me improve this. You guys can always tell me, like, what helps you guys. But I'm thinking maybe I'll start doing, like, a checklist. Like, during class, you can get bonus points. And it's kind of an honesty system. It's kind of like the honor system. But helping your classmate, you get 10 bonus points for that. Answering questions 5 times during class, you get 10 points. I don't know. Then people, it might be too much. I don't know. I have gotten the complaint. Brian randomly saying so-and-so gets points is confusing and gets me off track. I keep hearing you get points and you get points, and I'm confused. He sounds like Oprah. I get that every so like you get points and you get points. But I think that's too much. Yeah, I know. I agree, Devin. Right now the system I have works pretty well. So I try to revise it a little each semester. Yeah, I know. Yeah, so I'm always, yeah, and there's always going to be people who don't like the system. There's always going to be people who are like, I don't like this. I'm like, I try to make it fun. I want you to enjoy class. I tried. So there's our equation. Yeah, we did some of those. We can do this. We can do those after this, Keaton. You got it. I'm reviewing for the exam. Can you go over this systematic and stratified? Systematic is when we take every kth observation from a random starting point. So systematic is when we take every kth observation from a random starting point. And stratified acknowledges differences between the group, and then we sample in accordance to those differences. So it's very important. Devin, amazing work right there. Yep. Devin, great notes. Yep. Yeah, we can do the homework next. We'll finish off this homework, then we'll do the next homework. You got it, Thomas. because I think we only got one more question after this. We'll finish this homework since we started it, and then we'll do the next one. You got it, Thomas. I think people doing it. Like colors of M&Ms, you would stratify by color, but I would probably stratify by like flavor of M&M. Stratifying, you can stratify by color, but we probably see more differences with M&Ms based on flavor, and that's a bigger difference to acknowledge. You can still stratify based on color, so I would probably stratify on, and so that's the margin of error I just figured out. I'd probably stratify on flavors of M&Ms. That's my classic example there. And then I'd cluster sample based on bags. Like a bag is a cluster, but flavors of M&Ms. You're welcome, Camden. 100 points. Don't mind the question. It's awesome stuff. So this is 9.95 when rounded, or 9.948, I think it said. And so let's go take it. This is the margin of error. We have the center of the interval. We have the margin of error. We've calculated our interval. We go back to the question. It wants the 95% confidence interval. So we copy this. We say 325 plus this, 334.98 rounds. Is that it? Let me double check. Got it? 315.05. There we go. Got it. What assumptions do you have to make for this inference? I always hate these questions. Random and is not biased. See, none of these make sense. We didn't talk about anything about independent, not multimodal. Oh, wait. The hot dog weights are independent. The distribution of... They're using random and independent interchangeably, aren't they? By independent here, they're meaning random. You mean question. How many? We took a sample size of 50? Not today, my Pearson. Not today. So the reason is we have to assume they're mostly normal. They're tricking me here with this random, but then I read the rest of this, and I was like, okay. I wish it went over it more in the traditional sense. Is the randomization condition satisfied? We don't know, but it's reasonable to assume. That's a horrible answer, but it's right. I've done this one a few times. Is it 10% condition? Why is 10% satisfied right here? Oh, wait, Hannah, did I confuse you, Hannah? So let me slow down. I was looking down for a moment. The 10% condition is satisfied because these hot dogs are less than 10% of all hot dogs. These hot dogs are way less than 10%. Calculate the 95% confidence interval. Yep, let me show that again. So the key to calculating the 95% confidence interval is to mark all of your notation. Where are you at on this? Do you have all of your notation marked, Hannah? And have you identified everything right here? There are numerous hot dogs, I agree. I'd love like a hot dog sausage or something. Like with sauerkraut, and onions and mustard. Yeah, plus or minus the margin of error. Yep. This right here is the margin of error. And that calculated to this when I found it. Just be very careful. And people are saying, how do you do it on the TI calculator? This is found via T interval. And you know what? Let's drop it in the chat. Give me a second here. I do have ads on these videos. People are like, why are you putting ads videos in the chat? This question makes these questions a lot easier. Can't find it. Let me find it here. I'm live on YouTube right now, it says. 2 seconds. Ooh, got a lot of people still watching. Good job, everyone. TI tutorials. T interval. Where's my T interval one? T interval. T interval. So here should be the video for the T interval. There's a whole bunch of TI tutorials on everything. You got it. Awesome job. The C level is going to be whatever it says, like 0.95 or 0.90. It looks like you're doing it on the calculator right there. Neeland, it'll be whatever you put in for it. It'll be whatever you have. I'm too afraid to hurt I'm going to let this run in the background here. I'll try to remember 1 minute later to stop the video. I don't want to hurt my watch time because they like track watch time on videos. So I'm like, oh, if I start the video, I can't let my watch time be too short or else they'll be like, you didn't get it. And I'll show it in the background here too. So what you have to do is you go to stat tests and you go to T interval. We're watching Brian Inception right now on this. Still watch the video if you want. You don't have to. So you don't have to see the ad if I'm doing this. So you enter in here the sample mean. It does call it X bar, which is the sample mean. You've got S sub X, which is the standard deviation you'd put in. You put in the sample size and you put in the C level, which is the confidence for the interval. And then you just read through the question, mark your notation, and you got it. And doing this on the TI calculator right here will solve for it. Smash like, watch the video if you want. Sorry, you'll get an ad, but it's in this video now if you don't want to watch the ad. Click on any of the other videos if you want to see how to do any of the other things that we'll be doing in this class. But I made a video for each one that's very short. They're all like 1 minute, 30 seconds, because a lot of people did it in way too long of a time, and I didn't feel like they spoke clearly, or they showed like a good example problem. So every one of these shows you different things for different chapters and shows you how to use the calculator, all in a standardized format. So I tried to make some videos here that would help. We will have to know how to get the T without using the website. Nope. Good question, Hannah. There is a way. It's inverse T on the calculator, but you would not be required to do that on the test. So you wouldn't do that. We will give it to you. We just don't expect people to do that. We expect you to know how to use the websites and do that right there. The video is almost over. So, and we only have a few more questions. End video. End. I will let it finish off here. So once again, I made these videos to help out with, just going through. Yeah, email me, B. Stevens. This link no longer works. They removed the ability to click things on YouTube. Used to be able to put a link there. So these are less than 10% of all the hot dogs. Is this nearly normal? It's a large sample size. I'm sorry. These questions, I hate that it's like we don't know. That's clearly explain what the interval means. I am 95% confident the true mean weight of the hot dogs or the true mean sodium content of the hot dogs is contained in the interval blank to blank. So we are 95% confident the true mean sodium content of the hot dogs is contained in the interval. There we go. Make sure to use the interpretation you have. Last question on this one, then we're going to go back into the other homework. Will your flight get you to your destination on time? We've got flight times. It gives us all the info. Here's N, here's Y bar, here's S. So the only thing we need to solve our interval now is what? The only thing we need to solve an interval now is what? What is the only thing we'll need for the interval? Go ahead and look at the equation again. The only thing we would need for the interval, it gave us N, it gave us Y bar, it gave us S. So the only thing we would need for the interval is what? T. You could say degrees of freedom also, but we'll need the T. Are all the conditions met? I'm going to go ahead and say yes. Thank you, my Pearson. Condition 1, randomly select the flights. Condition 2, less than 10% of all flights. Condition 3, the distribution is nearly normal. That looks pretty good. We've got here a sample size of 72 flights. That's pretty normal. So considering that we have a decently large sample size, the large enough N condition would say this is mostly normal, mostly unimodal, tiny bit of skew, but since the sample size is way more than 25, we have the large enough N condition met, which satisfies the nearly normal. Little confusing there. Condition 3 is one of the longest ones to talk about, but it's that the shape of the distribution of the sample mean will be nearly normal due to the large enough N. It's like large enough N is a subtype of nearly normal. We didn't get QQ plots for normality, normal quantile plots. We can view the histogram. Looks unimodal and symmetric. Good. So now we just plug in the data. We've got here a sample size of 72. Let me copy this. Copy data. Okay. So the one thing we don't know, we don't have degrees of freedom now. Degrees of freedom is equal to 71. And now we need the T statistic. Was it 95% confident? I think it was 95, right? What was confidence level? 99. 99, that's a big confidence level. So let me hop over here and grab my T applet again. 99% confidence with 71 degrees of freedom. This is not a 99% confidence roll. This is. Be very careful in the way you're displaying it. It'll change the way the numbers are. Why is this a confidence roll? Because the confidence roll shades the middle portion of the curve. So make sure when you put in which thing you're selecting, this right here is a less than test. This is a greater than test. This is a two-tailed test. And this is a confidence roll. I'll talk more about this tomorrow, that this is the less than test, greater than test, does not equals test. And this right here is your confidence roll one, the one we use for confidence rolls. So the T-score is 2.647. So now that we know the T-score of 2.647, we go back to here. And we solve. We have every number we need now. We write out our equation of y bar plus or minus the t with n minus 1. That's subscript, so we don't actually solve that. S over square root of n. So this is 24.555, really, my Pearson, plus or minus the t statistic of 2.647. Do not use the subscript. It's just there to tell you what the degrees of freedom are. The S will be 2.55473, and then we do square root of 72. Now, when you solve this, I usually go square root of 72 first, because I'm going to find the square root of 72. Then I'm going to utilize that by copying it, 2.55473 divided 2.55473 divided by it. That is now the standard error. I multiply the standard error by 2.4647. There it is. That is now the margin of error. And usually, let's go ahead and write this down here just so we can see. It's going to be 24.5556 plus or minus the margin of error, which we just observed. We just observed the margin of error of 0.79 or 0. It's very close to this. Sure, I'm going to write out. There it is. We'll see as we add this in. Double check. And then a 9.5. It's more than enough decimals. Let's take a look. Let's go back to the assignment. And it wants the interval. So we're going to take the margin of error here. We're going to go the mean minus the margin of error, 23.76. And then we're going to go the mean plus the margin of error, which I had stored in there, 25.35. We hope, cross our fingers, not today, my Pearson. Interpret what this interval means. I am 99% confident the true mean flight time, or the true amount of time a flight is delayed. I'm 99% confident the true percent of flight delays on a certain days. I'm 99% confident that the true percent of flights delayed is contained in the interval blank to blank. We can be 99% confident that the interval contains the true mean monthly percentage of delayed flights. So they're looking at the monthly percentage of delayed flights. That's what they're measuring. That's got it. I am blank percent confident that the true blank is contained in the interval blank to blank. Did anyone get 100 on this homework? Do we have some hundreds on this homework? I think we're going to hop into tonight's homework now and review it. We did a little bit of tonight's homework yesterday, so that's why I kind of did this one right here, so people can get a head start on it. Did anyone get hundreds on this one? And let's hop into tonight's homework. Tonight's homework is confidence intervals for the proportion. Let's see. 100, nice job. Did it, like, I know we did that chapter quickly, but we kind of did it at the start of class, and then we did it at the end of class, and we covered confidence intervals a lot yesterday. So does it kind of make sense that you're not doing a confidence interval for the proportion anymore, you're just doing a confidence interval for the mean. So it's just a different formula, same idea of confidence intervals. That's why we went through a longer talk yesterday on confidence intervals, and it's just for different data. Yesterday was categorical data, today's quantitative data, and you just make a confidence interval, and it's the same sort of ideas of how to interpret them. And that's why I said, like, that most important talk I gave yesterday for, like, the remainder of the semester, there's green on my shirt, that most important talk for the remainder of the semester kind of sets the pace. Yep, I can do that next. So we'll knock out the homework here, Josh, and then we'll do the quiz. How's that sound? So let's do the homework, and then let's knock out the quiz. So we'll go homework, quiz. Here we go. So what are we gonna say? Can anyone, like, pause the video right here and try to figure out what we would say right here? I am blank percent confident that the true blank is contained in the interval blank to blank. So a few of these sound ridiculous. This doesn't even give a confidence level. That's ridiculous. This right here is talking about the random samples. We don't talk about the random samples. And Alyssa is right. It's C. Because this sounds a lot like I am 95% confident that the true population percentage, which is what we're talking about, of orders placed on the internet that will arrive within 3 days is contained in the interval blank to blank. Now, it's not exactly what we say, but it's because you can change it. Now, don't change it too much or else you'll say something really crazy. But it sounds very similar. So when you look at these, this one right here doesn't even give a confidence level. It just says this is what will happen. but our confidence level is 95. They didn't even state their confidence level. What do you? No, you didn't give me your confidence level. Give me your confidence level. What are you confident? How confident are you? 95% of the random samples. What is our confidence interval trying to estimate? The random samples or the population? Our confidence interval, is it trying to estimate for the random samples or the population? For the population. So this doesn't make sense. 95% of the random samples. No. Much less than that would show this, but also it doesn't make sense because we talk about the population. One can be, almost like I am. I'll change that to I am. I am 95% confident that the true population proportion of orders that arrive within 3 days is, I'm going to change that to contained. I am 95% confident that the true population proportion of orders that contain within 3 days is contained in the interval blank to blank. That is definitely correct. That is 100% correct. It's slightly different, but it's just synonyms and stuff like that. Like they're doing the same context that we do when I give you the form way of doing it. Just so you can see again, my form way of doing it is this right here. Can I go back in time on this? Got to go way back in time. So this is the form way I do it right here. So this is the form way I do it right here. I am blank % confident that the true. This is the part where usually people make mistakes when you have to write it on the test, because that part right there is the longer part where it says the true population proportion of orders that would arrive within 3 days. People usually just say true mean or something. They don't give it the context. So if we were doing a written test, I'd spend a lot more time focusing on making sure you can write it. I just say like, well, what are you talking about? And they'll say the mean. I'll say, well, what mean? They'll say population mean. I say population mean of what? And they'll say the population mean of how much students weigh. I'll be like, yep. I am 95% confident the true population mean of how much students weigh is contained in the interval blank to blank. No, so I don't know, just practice. One is 95% sure that between 70 to 86% of the orders placed by the sample customers arrive on time. Do you see this right here? In our formula, which we still have on the screen, that is p hat. I still have it highlighted. This is p hat. And the next thing, the plus or minus, is the margin of error. Look at the problem. That is p hat. That is the margin of error. I'm 95% confident that the sample customers had this. My sample customers had what % of their orders arrive on time? My sample customers had what % of their orders arrive on time? Hint, this is p hat. That's the sample proportion. So I know this. I know what my sample proportion is. That's what my sample proportion is. You don't make an interval to estimate your sample proportion. You know what it is. I know my sample proportion is this. I'm trying to estimate. You could say sure. That's fine. If you were to write it out, you can say I'm 95% sure. Yeah, it's about the same as confident. Like, how sure are you? 95%. It's fine. Different disciplines might say it differently. That's why I don't worry so much. A long time ago, someone was like, why do you make us say everything the same way? And I'm like, just to make sure people don't say crazy things. Not like crazy things, but like if I don't standardize it a little bit, then someone will come up with a way of saying it that's so different. They'll say like, do not write this down. They'll say like, I know 95% of my data is for the true proportion between the intervals of blank and blank. I'd be like, that makes no sense. They'd be like, well, it's yeah. I feel like that half makes sense, but I'll be like, I'm going to hit the computer. Really, what are you saying? So that's why I like to say I am blank % confident that the true blank is contained between the blank to blank. So yeah, there's a 95% chance that on any given day, does this want to know about days? It doesn't. It wants to know for everything. So this is not correct because we're not asking about days. We're asking about the population parameter, which is for everything. So we're not asking about certain days. We're asking for everything. This one right here, we need to identify our notation. Once we identify our notation, this becomes a very simple problem. I'm also going to drop in the chat right now. I should have kept it up. I'm going to drop in the chat a video. I'm going to ruin my analytics. I'm not going to play the full video for once. Ruin my analytics. I care too much about that stuff. It's like I've got the most booming YouTube channel ever. One proportion Z interval. One proportion Z interval. Okay, so if you want to do this on the calculator, check this out right here. This video on the calculator right here will show you how to do the one proportion Z interval. It can be a little tricky. Not every problem is solved instantaneously on the calculator. The calculator can kind of help you do these things. And yes, so who can tell me in the chat? Who can tell me in the chat any of the notation for this problem? What is any of the notation for this problem? We need help with notation here. There are two notation things to get. There are two notation things to get mainly. 3,000, Alyssa, amazing job right there. What are some of the notation? N equals 100,000. You're right, Hannah. That is the sample size. And then the other one, a lot of people forget. A lot of people forget the other one. A lot of people forget the other one. The other one is X right here. The other one is X. You got it. And so I'm going to do this a little bit quicker because we did this again yesterday. And I do suggest maybe checking out the video if you want. You don't have to, obviously. Let me stop the video here. Yes, I did play for just a moment because I don't want to ruin my analytics. So I couldn't help myself. Can't ruin those analytics. So N equals 100,000. X equals 4867. What can we find from X and N? X over N equals P hat. And so we get right here that 4867 over 100,000 equals to this. And we put in here 0.04867. We can find here Q hat. We're going to do chapter 13 quiz next. You got it, Tyler. Yep. So that's P hat, Q hat. My Q's look like threes. Q hat is equal to 0.9. It's just 1 minus P hat. 5133, if I'm doing the math right in my head. And then we do the formula right here of, and I can't remember what confidence it wants. What confidence? 99%. The Z-score for a 99% confidence interval is 2.5758. 2.5758. And so we know the Z-score. I'll show it here in a moment. And then thank you very much, Alyssa, right there. Alyssa, you got 300 points. Thank you very much. I was like, I think it's right. And then we go here. We put in the numbers, 0.04867 plus or minus 2.5758 square root. Oh, my gosh. 0.04867 times 0.95. Oh, that's that number there. I'm very sorry. It's so I can't write. I hate my handwriting. The problem with this problem here is it's very hard to do without a calculator because there's so many small decimals. This formula, just so you can see, I'm going to write it in like the notation. It's P hat plus or minus Z P hat Q hat over N square root. So, yeah, you can use software or anything to find the Z-score. You have to use David M. Lane. This one, you can do it on this one. Please tell me if you're off by like a decimal or two. If you're off by like a decimal or two, what's 1.645? There it is. I think it's on the screen right now. Why is it not? No, it's not on the screen. Ooh, my green screen's not green screening well. Really green screen? Oh, that's working better now. Okay, cool. 1.645, and you can do this right here by going to the two-tailed. We're on the Z, and you would go here and enter in 90, and there is the Z-score Thomas was looking for, 1.645, and then if we want a 99, and I know the extra decimal is 2.5758, so that's the Z-score right there. I have to fiddle with the green screen later. And we go back to the problem. There it is. But I do like that I basically have this written into R. And so if, let me see right here. And that's a long way to solve it. Well, we can put in the, Peel gave me the P hat. There's sample size, there's Q. There's my interval. There is the interval. Where people make a mistake on this one is they don't change it to a percentage. And so be careful. That's 5.04. We can memorize that. And there it is. That's got it. All this was right here when I solved it in the program is I was just solving this equation. Sorry for the very, very sloppy handwriting. Do you guys see how to get the z-score? Sorry, let me scroll down the chat real quick. I think you'll see. Hannah, do you know how to get the z-value on the normal curve? Which one? Could you just memorize the z-scores for the most common? Here, wait 2 seconds. Right back. I'm back. What's happening? Yeah, use the David M. Lane to find you can use David M. Lane. Let me show David M. Lane real quick. So the David M. Lane, what I would do is I would enter in this one right here. I'd go to between, and then you can go to 90. And so the z-scores you are seeing, you just change this percentage right here from like 90 to 95 to 98. Did I get it right? Oh, that 98%. Actually, let me retract that message. 2.3263. That's what it is. So 98 is 2.3263. There it is right there. So you can use software, anything. You will not have to memorize these for the test. I will give them to you, so you do not have to memorize these or anything like that. So you can use David M. Lane. You just put in the area on it, and then you do the between, and it'll give you the answer. There's multiple ways to get it, so be careful. Just know how to solve it one way. As long as you see what's going on. Does this make sense to everyone? Like Sam and Keaton and Hannah, do you guys get it right here? Do we calculate it with 90% z-score to left and right? Hannah, I'm slightly confused on that. Are you saying, do we calculate it with our 90%? What does your question say, Hannah? Does it want a 99%? What does your question want? Does it want like a 99% confidence roll or 90%? If it says calculate a 90% confidence roll, the z-score will be this. So you only take one of these numbers right here. It just gives you the positive and negative of it because it's like the plus or minus. So if it says 90% confidence, only use this right here. But if the question said 99% confidence, it'd be this right here. If you notice, the interval gets wider as we go to more confidence. Is this number right here is the z-score number. So these numbers that we're finding right here are for the equation. this Z number we put in. Does everyone see where the Z is at? This Z is related to the percent confidence, like where we did at the very end of class. We had y bar plus or minus a t with s over square root of n. So both of these right here tell us the confidence level. So that's kind of a review right there. So you have to plug in all of your numbers, and it's a kind of harder solve. I know I scribbled the numbers up here. That's such scribble, scribble, scribble. But these numbers right here would be p hat and q hat right here, and they're so long to write. My handwriting will look horrible if I try to attempt to write them again. What was the link for the Z again? You got it. I'll put David M. Lane in the chat again. You got it. Good question right there. There's the David M. Lane link in the chat right there for you guys to click on. But these give you the percent confidence. So if it's 68, Z is usually like 1. If it's 95, Z is like 2. And as you go more and more confident, Z goes wider and wider and wider. Good questions. Good questions. Good practice. It's all about the practice. And now we go back to the questions. Do I think 5% is plausible? Yes, because it's in my interval. I think 5% is plausible. So we've got right here, children with vitamin D deficiency. We've got that we have notation. I need your guys' help. I need you guys' help. I need some notation. Who knows any of the notation? Is it 98? Cool. We'll calculate the interval. Who knows any of the notation for this problem right here, right now? What notation do we have for this problem? I need you guys' help. Try to pause, try to watch, and be like, what is the notation for this problem? We've got a bunch of numbers right here. Got that, got this, and got this. What is the notation for this problem? Oh no, Keaton, maybe post what you got, Keaton. I'll look at it. You got it right there, Elizabeth. Nice work. Elizabeth, you had 200 points if I haven't said it today. Great work, Elizabeth. That's N. Yeah. It's just not, it's nothing. It's nothing. Zulon, you're totally right. And nice job right there. You identified, and technically this is P hat and then Q hat. And so it'd be P hat right there. Because it's a sample proportion from a sample size, and then Q hat is equal to 0.078. So just small technicality on it. Don't worry. Like, I'll leave it. You'll catch me eventually. Where I'll write P or P hat, and remember P hat is for the sample, and this came from a sample size, so it's a sample proportion. So it's very, very small technicality. But still, like, if you were to accidentally, don't do this. If you were to accidentally write your formula like this right here, it's wrong. Nice job, Keaton, right there. This formula is wrong, but if you wrote, you could solve it. It would still solve. You just need your hats. So that would solve out if you made wrong notation. Just you would have to just follow through on the follow through on the wrong notation. If you get what I'm saying. Yeah, it's P hat. It's called P hat, which is like an estimate. So like the hat on it, like when you look at the Y hat is like an estimated Y, which comes from the regression line. So the regression line makes the estimate, and then the Y is the actual. So it kind of goes by the same thing, because the P is the actual, and then the P hat is the estimated or from the sample. And what do we get an estimate from? From the sample. So the P hat is an estimate from the sample. The Y hat is the estimated from the line. So the Y hat is an estimate where the Y is the truth. The P is the truth where the P hat is the estimate. So it goes on along the same thing of put in the hat means estimated, and it's from a sample. And so Y hat isn't really, I guess it's from a sample. It's from a model made from a sample. Good question, Elizabeth. Yeah. It's like, well, why do we put the hat on it? It's a general notation used for estimate, and the estimate comes from a sample. Good questions. And you wouldn't believe this. I mean, you'll believe it. I'll say it. A student was the one who told me that the hat generally means estimate. Like, they looked up what the notation meant, because I kept saying sample, and they're like, well, what does it mean, sample? I'm like, yeah, the hat means sample. And they're like, well, why is Y hat? Is that sample Y? And I'm like, and they're like, they looked up and it means estimate. And I said, oh, well, the Y hat is an estimate from the model, and the P hat is an estimate from the sample. That's what it means. It's an estimate. Great questions. It really is student questions that have increased my knowledge of these concepts. As students keep asking why, I keep investigating. Students like, well, why this? Why that? I say, I'll have to look into it. And if a student says I'm wrong, I say, oh, wait, I was wrong? Because I'm wrong every once in a while. If Elizabeth was like, Brian, you're wrong, I'd say, what am I wrong on? You got it, Erica. 2 seconds right here. Wait. Would you guys mind if we come back a little bit later? I'll do a stream later. How's that sound? We'll do it. I'll come back on and I'll put in the videos. Does that sound good, everybody? I will come back. Brian will return. I'll see everyone. I'll be back in about 30 minutes. Bye, everybody.